Okay, good morning, ladies and gentlemen. I'm Helen from Department of Chemistry and Nanoscience at Ewha Women's University. Welcome to the first international conference on Empower Women in MOFs and Beyond. Okay. Okay, the idea for this meeting began at EuroMOF 2023 in Granada. It was a highly successful conference filled with inspiring plenary and keynote talks and an impressive number of participants. But as that event came to a close, some of us sensed that, paradoxically, within our rapidly expanding MOF community, certain voices and presences seem to be fading or becoming smaller. Among those who felt this most keenly were Irichi and Patricia. Around the time of the EuroMOF closing ceremony, Irichi approached me and said, "Why don't you launch the Women in MOFs?" And so, together with Irichi, Patricia, Catherine, and Nancy, after 2 years of a discussion and preparation, we are finally gathered here in Mexico City. MOFs have now become undeniable global trend. This year, the field was even honored with the Nobel Prize in Chemistry. And MOF research continues to get bigger across multidisciplines and applications. Within this tremendous wave, each of you plays a truly important role. As Patricia pointed out yesterday, the higher we climb in the academic hierarchy, the fewer women we see. The sustainability of talented researchers should never be threatened by gender, region, or any other barrier. I have always believed our MOF community to be one of the most open and forward-thinking in science. But through this meeting, I hope we can reflect once more on where we stand and find renewed strength in one another. Since this conference was organized directly by professors without professional conference organizers, some aspects of a preparation may have felt a bit slow or inconvenient. I sincerely ask for your kind understanding. Now, please enjoy the first international conference on Empower Women in MOFs and Beyond from Mexico City all the way to Merida. Thank you. Okay, and now it is my great pleasure to invite a special guest for greetings, Dr. Soledad Funes, Head of Scientific Research Coordination at UNAM. Please.
Which one should I use? Is this one okay, or is this one is better? Okay. Good morning, everyone. Welcome to Mexico City. Welcome to UNAM. Bienvenidas, bienvenidos. On behalf of UNAM, it is a true pleasure to welcome you to our university. I would like to thank the organizing committee for choosing the Instituto de Investigaciones en Materiales as the venue for the first stage of the Empower Women in MOFs and Beyond conference here in Mexico City. Our university is deeply committed to advancing knowledge, fostering collaboration, and promoting equality. Having this meeting begin here at the heart of our central campus reflects our aspiration to connect science with society and to make knowledge a shared and transformative force. We are honored to open the doors of our university to such a vibrant and diverse community of scientists as we have today. It is a great honor also for me to join you today for this opening, although I understand that the real kickoff of the meeting was yesterday, but still, thank you for the honor you are giving me to talk to you today. We are especially delighted to welcome speakers and participants from more than 10 countries across 3 continents, whose presence underscores both the global reach of this initiative and our shared commitment to building a more inclusive scientific community. Despite the progress achieved toward gender equality in science, we know that the path ahead remains long. Women still represent only about 1/3 of the researchers worldwide. Yet, inequality in science is not only about numbers or gender. It is also about the diversity of perspectives, disciplines, and life experiences that are often left out of the conversation. When women's voices and those of other underrepresented groups are absent or undervalued, science itself becomes narrower, less creative, and less capable of understanding the full complexity of our world. This conference was conceived precisely to confront these challenges, to celebrate and amplify the voices, creativity, and scientific achievements of women, and to recognize the power of diversity as a driving force for innovation, collaboration, and discovery. MOFs, as I'm sure you know better than I do, are among the most fascinating materials of our time. Crystalline porous architectures that have revolutionized how we think about gas storage, catalysis, sensing, clean energy, and environmental remediation. Their versatility has opened new frontiers in sustainability and technology. A testament to the impact of this field is this year's Nobel Prize in Chemistry, as Nancy already mentioned, awarded for the development of metal organic frameworks, a well-deserved recognition of the profound influence of MOFs on both science and society. We are deeply honored that two of this year's Nobel laureates have graciously joined in inaugurating this conference, demonstrating not only the global relevance of this meeting, but also their personal commitment to advancing diversity and inclusion in science. UNAM is proud to host this event as part of our mission to promote excellence in research, technological innovation, and gender equality. At UNAM, we believe that science thrives when it is inclusive, when every voice, perspective, and talent has a seat at the table. Through the activities of this conference, workshops, mentoring sessions, and roundtables, you will foster mentorship, collaboration, and dialogue. These connections will not only strengthen the MOF community, but also inspire the next generation of women scientists to pursue their passions with confidence and purpose. I would like to express my deepest appreciation to the organizing committee for their dedications in creating such a meaningful platform, to the team at the Instituto de Investigaciones en Materiales, and to all of you for your ideas, your knowledge, and your example. Let this week remind us that when we empower women, we empower science itself. May this conference spark new collaborations, inspire new discoveries, and help us move toward a more equitable and sustainable future. I wish you all a very successful and inspiring conference. Thank you very much.
Thank you very much for your warm greeting. And now it's time to start the second day of this conference. Okay, let me introduce the first speakers. Okay, so let me introduce the first speaker, plenary speaker. Okay, Conchi Ania, sorry. Okay, so let me introduce her briefly. She received her PhD degree in chemistry by University of Oviedo in Spain in 2003 and performed her postdoctoral stays in City College of New York and France, CNRS. And after that, in 2017, she joined the CNRS as a research director, where she is the head of NAFMET group. Actually, she received a lot of the awards and honors. Among that, I want to highlight one. She received the National L'Oreal UNESCO 2008 Research Fellowship for Women in Science. I think the perfect title for this. Okay, today she is going to talk about catalytic conversion by using the nanoporous carbon-based heterojunctions. So let's welcome.
Thank you. Thank you very much. I think I can just hold this one. Let me just put on my clock because I am very bad at keeping timing. And I have in the other side the pointer. Yes, thank you very much for this kind introduction. Muchas gracias a todos. Y gracias por la invitación. I'm going to switch to English again, but I thought it was interesting since we're in Mexico and we speak Spanish, just to say that it is very interesting for me to be here today. It's been a little bit more than 20 years since I defended my PhD. And to be honest with you, I think I've never thought about the future, how that will be after doing the PhD and what opportunities I may have. And of course, I would have never pictured myself like giving a plenary lecture in a conference like this. So I'm very proud of this. So thank you, Patricia, for the invitation and all the organizers. Today, what I'm going to do today is I'm not going to speak about MOF, I'm sorry, but I'm going to speak about some other fascinating nanoporous materials, which are carbon materials. So for those of you who are not familiar with the carbon materials, I like to start when I have an audience like that. Just as a reminder, I'm sure that most of you have already heard about any of these different allotropic forms of carbons, graphene, graphite, carbon nanotubes, fullerene, or diamonds, which are not the most important ones, depend on the perspective of the speaker, of course, but just for you to consider something that is that all these materials that you have in here, they have a very different properties. And one of them, if we pick the graphite and diamond, is just not only their crystallographic structure, but also the fact that due to this different nature of the carbon atoms to be bonded to each other, we can have very different properties from electrically conductive to isolator, from transparent to opaque. And this is the richness of different carbon materials. So if now we allow the carbon materials, the carbon atoms to get to bind not only to themselves, but also to some other heteroatoms, we can have, and this is important that this is not an exhaustive list, different forms of carbons in some of the examples of the family of carbon materials. We go from carbon blacks that we all use in the ink of our printers, to glassy carbons, to porous carbon materials that we also use very regularly in the barbecues, to high-tech carbon fibers and nanofibers, which are a part of many carbon-carbon composite materials in the aeronautics industry. Also diamond-like carbons, diamond, carbon nitride, of course, the carbon dots and graphene oxide and all these derivatives. This is just for you a glance of the different carbon materials that we may have. But now I will introduce you my favorite ones because I've been working with them for more than 20 years, which are nanoporous carbon materials, amorphous nanoporous carbons, which is the beauty of them, but also the challenge. We don't have a regular structure as those in crystalline porous materials. We have a completely disorganized structure, which is what I've tried to illustrate in here with some high resolution TEM, where you have these turbostratic or twisted graphene layers of the carbon materials, which can be mingled with also some other structures. As you can see in here, these are the lines were drawn by me just to show they oriented another graphitic domain in the carbons. We can have both of them coexisting at the same time. The challenge is how to control them. And we also can have pores in between. This is what you can have in here. These light areas, gray light areas correspond to the pores in the nanometric dimensions. The importance of this structure is that if we analyze this in the high resolution TEM, what we have is that we are far from the perfect sp2 with hexagonal structures of the graphene layer. We have a lot of defects formed by 5 to 7, 8 member rings in the aromatic structures, which are in fact responsible for this twisting of the materials. And these defects or topological defects are in fact the reason of their high reactivity and the interest of many catalytic applications that I will show you in a while. I would like just to mention something that it's in the world of carbon materials has been forgotten for many years. The early works in 1951 of Rosalind Franklin, which was an English researcher working in Paris, in France, and she was working with X-ray diffraction. And in her early paper, she described already how the structure of different carbon materials, how we have these domains that I show you in here of the oriented and other graphitic domains also connected to the disoriented one. A paper in 1951 that she was able to put up together owing to the high resolution XRD patterns at that time. So when it's a paper that has been forgotten for many years, and I'd like to show even for those who are not familiar with this community. So this is a glance of the materials that I will be speaking of today, some of them with applications with reactions, other not. And because I will not have time to speak about everything, but in any case, this is pretty much the outline. I will give some examples or how we do to control the porosity of these materials, which is very important. Also the surface chemistry and the defect topology. Then the core of the presentation will be also devoted to some examples on the photoelectrocatalytic applications with focus on the small molecules that I've mentioned. And also this is a new research direction that we're taking in the team, which is trying to profit from the light emission features of some of these carbon materials. In this example, I've put in here carbon dots, which are interesting for the nanometric dimensions, but we can also have light emission with nanoporous carbons. But unfortunately, we don't have time to talk about these today. I will focus in the first two, as I've mentioned before. And before getting into the details, these are the people that made this possible. So this is who we are, the staff. Right now, we are working in France, in Orleans, very near Paris, but without the traffic that Paris has. And this is important. I wanted to make a summary of from my very first PhD student, who is Belen, who is today also a researcher at an institute of research belonging to CSIC in Asturias, from Carlos and Gloria, who started their own company a few years ago. Those in red are those who are doing the PhD right now, and then we have some technicians, and we have also the different postdoc. I'd like to mention also, beyond the numbers of the gender that you can see in here are in favor of women, and I am convinced that this is because I am a woman myself. And yeah, it's always been like that. I may be biased, but on the other side, which perhaps is good to make the balance in science. But what's interesting also is to show you we need the different ways of thinking that come, of course, from mixing men and women. But we also have the different ways of thinking come sometimes from the different cultures. And so I've put in here just a summary of the different flags that we have. I've never have a student coming from Mexico to do the PhD or the postdoc, which is a shame. But as you will see in the end of the presentation, I have open position for next year. So if you're interested, just write to me. But we have people from Latin America. You'll see the Colombian and the Uruguayan flags in there. I think it is also important to have in mind that science is all about an open mind. This open mind is mixing the different way of thinking, women, men, but also different cultures, which are very important. They define the way we end up to a different points. So about the synthesis of porous materials. The synthesis of nanoporous carbons, actually, it's nowadays is an industrial process which is very well known. It's commercialized at a very high amount of tons per year of nanoporous carbons, and it's based on this process that I've summarized in here, which is the thermal conversion of almost any precursor that has a decent yielding carbon. It's a thermal conversion and followed by an activation with different agents, typically CO2 or water vapor. And it's a patent that was filed in the 1900s in different countries. You can understand that the patent is no longer valid, so it's free. And this is the process that is industrially used nowadays. However, there is always a however. The problem is that with this process, which is economically very attractive, we cannot control the pore size distribution of the materials. And this is where I like to quote this sentence from I think it was a Belgium Belgium architect, who used to say that the art of architecture in the buildings is to control the distribution of the holes. Well, in material science, particularly when one's worked with porous materials, this is exactly the same. How to control the distributions of our holes at the nanometric scale. And this is not easy with this commercial process that we have in here. So the challenges are in this direction to try to find new precursors and particularly new activation methods that allow us to control two different characteristics: the porosity, the size, and the pore volume, and also the distribution, in order to have narrow distributions and not so large as those that you can see in here, but also to have a very high volumes, depending on the applications, and control depending on the applications that we are looking for. So for many years, we've been working on a sol gel method in order to get carbon materials, which is the classic chemistry in homogeneous phase. This is just a summary of what we can do. We can change the composition of our precursors. That after all, we have a polycondensation reaction of an hydroxylated precursor with an aldehyde. We control the temperature conditions, and then we can have these different materials. We have the green gel or the carbon gel after densification, depending on what's your application. And for many years, we have been working on different aspects on these syntheses. The first one is trying to make them more mechanically compliant. These materials are very brittle, and what we want, which is a challenge, we want to do some electrodes, as you will see later, because they are very prone to fracture. We can also have the shape that we want. We simply have to change the reservoir of the synthesis, but we very often we have this kind of curvature, which also is also very much related with this lack of mechanically compliance. And so in order to have materials where we can control these mechanical properties, we have introduced several additives, as I will say. The beauty of these synthesis is that we can have two levels of porosity, and this is easily seen in here, where I have materials that we have prepared following this sol gel approach, compared to these that you can see here in green and in cyan, which are the gas adsorption isotherms of commercial carbons. These are, let's say, the 99% of the carbons that you can buy in the market. They will have this shape in the isotherm, so very high surface area, between 800 and 1,100 square meters per gram. But it's very difficult to have pores in the mesopore range, which, as you know, we could say that it's from 0.5 to 1. Only in the case of what's called the superactivated carbons, we can have this slope in the shape of the isotherm, which is indicated that we have large micropores and mesopores. But still, with this kind of synthetic approaches, we have in here, as you can see, the position of this loop, this hysteresis loop, which is giving us the size of the large mesopores, is changing. That's something that we can very carefully control. And we can also have a very high pore volume. So that's the beauty of these approaches. We can also have carbon materials that have a very rich surface chemistry, so that mainly hydroxyl groups and carboxyl groups, which may be interesting depending on the application. If we want to have an adsorbent that is interacting due to some pH acidic control, we may be interested in having these carboxylic groups. This is the distribution of the group is something that you can see in here in this thermal profile for different materials. The pristine, which is the orange one, that has different hams corresponding to the thermal decomposition of these groups. We also have, if we do a selective thermal treatment, we can get rid of the carboxylic groups and leave only the hydroxyl groups, and then in the end, we can also remove them all completely. This comes with a price. If we sacrifice the surface chemistry, we gain in the electrical conductivity, which is what you see in here, which for electrochemical applications is very interesting. The material that was in here with this double functionality of carboxylic groups and hydroxyl groups is non-electrically conductive, so we can add as many additive as we want, but it would be very penalizing to use it as an electrode. But if we simply remove those functionalities, what you see in here is an increase in the current density in this case, which is an indication of the fact that we are now able to electrochemically see the porosity that was already present in the material. The challenges were, as I've mentioned before, to how to increase the electrical conductivity of these materials if we don't want to sacrifice this surface chemistry. This is something that we did some years ago by introducing a carbon black as a conductive additive. These are the gas adsorption isotherms of the materials prepared with different amounts of carbon blacks going from 5 to 15 degrees. So what we observed at that time is that in terms of the porosity, the surface area and the microporosity did not change when we perform the synthesis in the presence of the different amount of the carbon's additives, but we changed the shape of this hysteresis loop that you can see in here. The pristine material is the green one, the GT, and you can see that as long as we are increasing the amount of the additive, we have the formation of a secondary pore network that it's appearing from relative pressures from 0.7 to 1, meaning that we, or implying that we have mesopores of larger sizes. If we analyze this data in these plots, what we can see is that, well, here is the specific surface area that in all the materials, they follow the expected values considering the rules of the mixture, so which is just the composition. But if we analyze only the pore volume, and particularly if we make a differentiation between the V1 and the V2, the V1 corresponding to the one already present in the pristine material, what we see is that there is an interesting trend on the formation of these pore volume, mesopore volumes with the amount of carbon black. The increase in the electrical conductivity was several orders of magnitudes, allowing us to use these materials as electrodes. And this is one of the examples of the disc electrodes that we prepared even after carbonization, and where we got rid of these rinking and mechanical issues that I've mentioned before. The incorporation of the additives also comes with a price. We have to optimize the characteristic of the additives. I have here examples of the same synthesis carried out in the presence of different carbon additives. Carbon black in this case, graphite, graphene oxide, and reduced graphene oxide with similar concentrations. We perform a mapping by using Raman spectroscopy, which is a technique very sensitive to differentiate the different types of carbon materials that we have, the different type of hybridization. And what you see is that when we go to a large amount of the conductive additive, which corresponds to these dark areas in here, we have an uneven distribution of the carbon additive, as you can see in there. The same for graphite, which seems to be pretty much related with the hydrophobicity of the additives. If we incorporate reduced graphene oxide or graphene oxide, we have a smoother distribution in this mapping, indicating that the additive is well distributed within the matrix, and therefore we're not going to have different behaviors, electrochemical behaviors of these materials. On the other hand, as you can see here, we also have an impact on the final porosity of the materials, depending on the hydrophobicity of the materials, with a very large pore volumes. Check that in here we have the pore volume is 1,000 when we introduce these reduced graphene oxide in some of the concentrations. Another modification of the synthesis that we perform was to, because the synthesis of sol gel is, it's very delicate in the sense that we have a lot of parameters that we have to control: the temperature of the gelling, the drying, the pH, the ratio of the different reactants that we use, and they usually polycondensation and aging in order to get those nodules of the carbon to grow and to get the pores. It can take between 1 week and in 2 weeks. So we came up with the idea of using photo assisted methods in order to reduce the time of the synthesis, and this is what we did. In this case, these are the freshly prepared solutions, homogeneous phase, simply the physical mixture of the reactants, and then we apply for 1 hour a UV at different wavelengths. This is an example only in the UV at 25 degrees C. So as you can see, the reticulation of the and cross-linking of the reactants, it was much faster compared to the 2 weeks that we had before. And then this opened us also a lot of possibilities to play around with the wavelength of the lamps and so forth. This was the first trials that we did by changing here the composition of the polyhydroxylated aromatic compounds that we use as precursors. You can see in here the formula, and the difference is not only the number of hydroxyl groups, it's also the number of reactive positions, which I've marked in here with the star, which is going to determine the cross-link. The cross-link in the end is what we see in the gas adsorption features. So you see, if we start with bisphenol A, we have a material that in theory or apparently does not have a porosity accessible to nitrogen. And then as long as we are changing these materials, you see that we have not only an increase in the amount of gas absorbing here, but also a shape in the adsorption isotherm with completely flat isotherms corresponding to macroporous materials or also to mesopores. You see the position and also the pore volumes change. I have left in here some of the textural parameters regarding the volume of macropores and the surface area. But what's important also is that something that is very interesting in carbon materials is that when we have pores which are blocked and the nitrogen gas does not enter, and therefore we have this kind of porosity of adsorption isotherms indicating that we don't have pores. If we record the CO2 adsorption isotherms at 0 degrees C, we can actually verify whether if the material is porous or not. And what you can see in here is that this material really does have the porosity. It's simply that the necks of those pores are small enough and the nitrogen was not able to see them. We also play with different conditions. Again, this are the compositions of the reactants. And in here, these two numbers or parameters correspond to the variations of the pH, which is the neutral pH or acidic, or also to the presence of a photoinitiator in order to make the reaction, because it's photoassisted, if you remember. We found very interesting performance of the materials. In all the cases, this is an example of this one, of a THBA that has a very rich surface chemistry and two reactive positions. You see, in terms of the porosity, it doesn't really matter that much which are the conditions of the pH or whether we have the photoinitiator or not. Although the pH seems to control the pore size, and the photoinitiator seems not to be very relevant, because the precursor itself, it's also acting as a self-photoinitiator. But what was interesting to see, and this is a feature not easy to obtain with carbon materials, is that rather than having this disorganized amorphous structure that I showed you before with all the graphene sheets twisted and typical from carbon materials, we started to see this arrangement with channels, parallel channels, which remind those obtained of the mesoporous silicas obtained from a surfactant, which is, it makes sense because we are also using a surfactant in the synthesis. But you can see in here that in the case of a THBA, the natural pH of this material, it's very low. So in all the cases, whether if we adjusted the pH or not, the synthesis was carried out in acidic media. And in all the cases, we have this order pore structure. By performing a tip analysis using NMR, we were able to see that the differences in the presence or not of these channels, in this case of PG, which is this one, you see these the 0, 0 compared to the H0, so these two. where we have this order structure and then this disorder structure, is that we have this peak in here coming from the arrangement of the surfactant molecules. So we have a higher cross-linking degrees that in the end, when we remove the surfactant leading to during the pyrolysis, we get these channels, these order channels that you can see in here. Very interesting also for this type of materials is that this is how they look like. Two examples obtained from THPA. You see beautiful mesopores with a very nice arrangement of those cavities. And this is the corresponding gas adsorption isotherms, which are very similar if you look at them. So in terms of the surface area, we get the same because the composition of the precursor mixture was the same. But then tiny differences in the total amount of gas adsorbed, but it's the position and the shape of the hysteresis loop that was attracting our attention. So we decided to further characterize these materials by analyzing the hysteresis loop. For this, we did a scanning of the hysteresis loop. This is what you have in here. By simply, instead of running the normal isotherm, we did the desorption at different saturation degrees. So before they, all the porosity of the sample is full of the adsorbate. This type of analysis, as you can see in here, it allows us to verify whether if the pores are connected or not. Meaning if we have a material which dependent or independent pore system, which may be important if we want to use them, for instance, for adsorption. This is the two extreme behaviors that I've shown you in here. You see, when we do the scanning for this material, we have a part which is being desorbed. This is what you can see in the scanning, but then it comes to a point where it meets the boundary desorption, and then it goes to follow the same as when we have the full desorption loop. And in the other case, what we have is that they scanning, they are almost following the same shape as in the full desorption scan. The meaning of this is that in here we have connected pore systems, so that there is a fraction of these pores that we can quantify with this type of analysis, that it's that is connected to small pores, so that they cannot be dissolved or emptied as long as we are running this scanning. In this case, all the pores are not connected, or they're not connected between them, or they are connected freely to the external surface, meaning that they do not depend on the state of condensation or filling of the neighboring pores in order to be dissolved. So the mesopores in here, they can evaporate freely. They do not depend on the neighbors, whereas in here, yes, meaning that the connectivity in these pores may be important for some applications, but may also be a challenge or limitation in some other cases. Then I will go to the second part of the presentation, which is to show you some of the applications that we have done with these materials that we have prepared. And I've let you in here a summary of the different reactions that we are looking at, that as you can see, they are related with the so-called carbon, water, and nitrogen cycles, which are the conversion of very simple molecules into water or CO2. Very simple, but also very resilient molecules. There is also a part of these porous current materials, which is, of course, very much related to the adsorption. This is where I started my research activities. So even though I will not speak about these, I cannot just not say anything about the possibilities of adsorption with these type of materials, particularly for water treatment, but also for gas separation and storage. But if we focus on these simple molecules that I said before, the simplicity starts to get complicated. And this is a crowded slide on purpose, so that you can see that there is many different things that can happen when we try to work with them. The first one corresponds to the reduction of CO2. You see, the reduction of CO2 is a very complex one that can actually go through many multiple exchange of electrons from one which is a very unfavorable one, to 8. And depending on these, we can have also a variety of different molecules. So controlling the porosity and the surface chemistry of your catalyst, in this case, in order to control the selectivity towards the different products, but also the over potential that you may need or the amount of energy that you need as an input is very important. In the case of water conversion, we have different reactions of interest. It's the same case, either oxygen evolution or hydrogen evolution, or oxygen reduction reaction, which is pretty much related to that also. So very difficult because of the reactions, because of the exchange of the different protons, sorry, the different electrons that you can see in here. And in the case of nitrogen or nitrogen derivatives, this is even more complicated. We have the same scheme of reactions that can happen along our system, but also we have another limitation, which is the solubility of nitrogen if we are targeting the conversion of N2. N2 is one of the most stable molecules. Breaking the nitrogen bond is very hard, but also we need the nitrogen to get solubilized, to get in contact with our catalyst, and this is a challenge. The other challenge is that we have the competing hydrogen evolution reaction. So if we target nitrogen, we most likely are going to have hydrogen if we don't control the properties of our catalyst. So I will show you now some of the examples depending on the different molecules. The first one is in water. And I will speak about the application of carbon-containing photocatalyst in water treatments, because it's been one of the areas where we have been working very much in the past years. For those of you familiar with photocatalytic applications, you know that this is mainly dominated by semiconductor, inorganic semiconductor chemistry in heterogeneous phase. So with TiO2, which is the benchmark that should be in here, yes. And then there is a variety of different semiconductors that can be used for different applications. Really, the imagination is the limiting here. But very often once, when we start working in this one, the question that you may ask is to yourself, or you may hear, is which is the best photocatalyst? Well, it depends on many things, but there's two different things that you should consider. The first one is the band gap, which is the energy that you need to give to your catalyst in order to generate the electrons and holes that will give you all the chemistry. And this band gap depends on the optical properties of the materials, but also on the position of the band gap, which is actually the meaning of this plot in here. In the end, this is translated also about how much solar energy or natural solar light you can use, or do you need to use artificial solar or artificial light in order to excite your photocatalyst. And for the past year, most of the research community working in photocatalysis is working on heterojunctions. Heterojunctions are semiconductors or hybrid photocatalysts which come from the interactions of different semiconductors, typically two semiconductors with different properties. And there is a very different types of heterojunctions, S, Z scheme, direct, indirect, depending on how these interface between the two semiconductors is built, and how is they, depending on how the flow of electrons from one semiconductor to the other, or the flow of holes among them, it's going to be triggered when you do the excitation. In any case, if you know which is the band gap and the positions, depending on which are the target reactions that you want to do, you can play around and have different compositions of your photocatalyst. I'm putting in here just some of the examples that we have been working lately with carbon nitride and porous carbon, a mixed oxide of tungsten and bismuth, and also some clay-like structures, also incorporating carbon nitride in the structure. So you see that this is the composition. But one thing that you can already observe is that depending on the composition, you have a marked change in the color of the heterojunctions, meaning that there is an interfacial
different types of interactions in this interface of the semiconductor. And this is what is going to give you a better efficiency or not for your photocatalytic application. On the other hand, when we deal with inorganic semiconductors, it's very much established that your band gap, photoactivity, and in the end, the efficiency of the reaction will depend on different parameters or different indicators, which are located in here. But when we incorporate some carbons in the equation, because they also absorb a very large amount of a fraction of light, which is not used directly in the photocatalytic application, we have the challenges to determine which are the photoactive sites. And the fraction of light, which is absorbed by the material and used in the reaction that we're looking for. So one of the basic aspects is the characterization of this band gap, of the optical characterization. And I'm putting you in here images of a bismuth tungsten oxide, which has been mixed with 2% in all the cases of different carbon materials. You see, again, the color is different. The morphology was not really changing that much because it was very, very small. And the first characterization that we can do in here, and these are examples for TiO2, but also for this bismuth tungsten prepared from a physical mixer or a hydrothermal synthesis, which you can see if we record the diffuse reflectance, which is an indication of the amount of light absorbed by and reflected by this system, is that depending, since the amount is the same, depending on the nature of the carbon material, we're going to have a very large impact on the absorption of light, particularly in the visible range. And also for the same composition, if we compare these two, depending on how we prepare our catalyst, the amount of light absorbed is going to be very different. So that's something that we really need to control. If we want to go further and describe the optical band gap, we use this experimental data to recalculate the graphical type representation. And I've chosen in here this green one because we can see that there is this absorption age of the semiconductor, but we have a second curvature in here, very interesting one, which in the end is what we see in here. So we have a mixed semiconductor that actually has two optical pathways that contribute to the photocatalytic impact. And then in here we have the band gap of the pristine semiconductor, very, very close to it. And this one second, which is coming from the second matrix. So when you analyze this kind of data, be careful in the interpretation because you can see sometimes the aspects coming from the different zones of your matrix. This is one of the examples of the degradation of a pollutant on this series of the pristine semiconductor and modified with 2 and 5% of 3 different carbon materials. This is the conversion over time. In the end, this is a kinetics issue. So the faster I have the degradation in this case, the better for the reaction. And then you can see that compared to the pristine semiconductor, in most of the cases, we have an improvement in the kinetics. So we reach 100% in this case, around 50 minutes compared to the 150 or so that we have for the semiconductors. So it becomes very interesting. In this case, we were not able to go over 5% of the incorporation of our carbon material in here because we started to have some formation of secondary phases in the synthesis of the semiconductor. This is what you have. You can see in here with these platelets, which are linked to the fact that we were changing too much the pH during the synthesis. But what was interesting also is that while we were using these best photocatalysts, which had the fastest kinetics, we were also able not only to increase the kinetics of the conversion of our pollutant, but also to lower the toxicity of the effluent to be treated, which in the end is very important when we are dealing with water treatment, because we want to focus not only on the main pollutant, but also on the intermediates. For the best of our photocatalyst, we also did some trials in Chile, which has a, even in the winter, a more strong illumination conditions than in Orleans. And then for many years, this is a collaboration with the University Autónoma de Santiago de Chile, and it was funded by EBCIT. So we want to do summer and winter campaigns with our best catalyst using a CPC, a reactor, as you can see in here. And what we observe is that actually our catalyst needed a threshold of illumination in order to be active, which was very much easily reached in Chile. Even in winter campaigns, you see the conversion, of course, is lower because simply the cumulative flux is may also be lower. The kinetics is much faster during the summer campaigns, but it was also working. And this threshold that I showed you before corresponds to a value which is lower than the average irradiation capacity that we get in Orleans. So we convinced the region to fund us to have this CPC photoreactor, which is also assisted by an LED so that we can operate, and we are now operating with it in summer and winter time, and to see whether we can do some photocatalysis not only in Chile or Mexico, where you are lucky enough to have a very high irradiation sources, but also in Europe when this is not like that all the year. Another interesting discovery that we did while trying to understand the mechanism of the use of carbon materials in photocatalysis is that they can also form excitons themselves, some of them. So when exposed to UV light and also visible light, we can have this kind of reactions in here. So we form holes in electrons that can interact with oxygen in the media or with water and form oxygen reactive species, radical reactive species, which are very interesting for photocatalytic applications. These are just some of the different techniques that we use in order to determine this charge transfer from the photogenerated electrons and hole when we irradiate the carbons alone in the absence of a semiconductor, and where we were able to see that some of them even have an amount of oxygen radical species which was higher than that or comparable than that formed by TiO2. And it was also interesting to see that those radical species are actually long-lived transient species. So we can have them in the reaction for a few hundreds or nanoseconds. And this is why they are important to interact with in the photocatalytic applications. I have 45 minutes only, right? So yeah, I should be finishing. So I will just mention a couple of slides more. The first one is this one, that based on this discovery that the carbons could be used in the presence of irradiation to generate some radical species, then we work with some industrial partners in Israel and in Spain in order to integrate them in a wastewater treatment plant as a tertiary treatment to induce the regeneration of the carbon that they use for the adsorption. So these are some of the trials that we carried out when they had the saturated granular activated carbon, which surface area was around here. And depending on how we perform the irradiation and the loading of the carbon with the water, you can see that we get almost the recovery of the surface area of the materials compared to the characteristics of the activated carbon before being used. If I have to choose, because I have no time, yeah, I'll show you what we are doing now, which is we're also using these kind of heterostructures, and which are built with titanium oxide, but also niobium oxide and their mixtures with different carbon materials derived from graphite, graphene, and graphene oxide, and so forth, for doing photoreforming of hydrogen. What we want to do in this case is that some years ago, we observed that if we expose these materials to light, and then you can see that we can have a very large increase in temperature. So from 23 to 43, this is a lot in only 2 minutes of irradiation and of these materials. So the idea is to combine their photocatalytic effect of the semiconductor in the heterojunction with the photothermal effect that we can get coming from the carbon material in the mixture, so that we can not only profit from the UV or visible, but also from the wavelength in order to get a heat and increase in the heat. So this is a project that we are now running. You can have in here the results, the latest results that we got concerning the formation of hydrogen from the splitting of water directly. When we are comparing the normal thermal at 200 degrees C, because we want to avoid the use of concentrators in order to go very high in temperature. And if we go with the 200 in light. And this 200 can be, this is just an example, the first trials that we did only with the carbon material, but we can reach 200 with the light very easily, depending on the composition of the materials. And then you can see the evolution of some of the catalysts. We still have to add platinum in the reaction because these are the first trials, but we are improving the efficiency. You can have here the thermal to photothermal ratio, which is extremely high for some of the catalyst by simply this capacity that carbon materials have to convert the fraction of light also into heat. And I am fortunately out of time, so I can now tell you about the CO2 electroreduction and or the NO3 electroreduction. So, but I will leave you with this, which is this is one of my favorite conclusions. I mean, we in different catalytic applications, we may not compete with the reactivity of platinum, gold, or palladium. This is not the goal. This is not our objective to compete with them. But also, there is one advantage that we have, which is the price. We are not a raw critical material. We can get a carbon and a porous carbon with control properties. That's another story. But we can get them from almost anything. And this is just a summary of all the different applications that, unfortunately, I was not able to to describe them all. When we have porous carbons, in this case, of porous materials in general. In the fields of environmental remediation and energy conversion. And as I said before, yeah, if someone is interested in coming to work to France with us, just don't hesitate to contact me. We will have opening positions for both PhD and postdocs in 2026. Thank you very much for your attention.
I have a question that you taught us that you can control the conductivity of the carbon by surface chemistry. And if you remove carboxylic groups and only leave the OH groups, the conductivity improves drastically. Could you comment on the mechanism behind why it happens?
The conductivity of carbon materials, it comes from the sp2 aromatic structure. So when you have the structure of graphite with only carbons, you have electrons which are delocalized all over the planes of the structure. When you put surface groups, which are normally going to be in the edges of those graphitic layers, or graphene-like, as we call them, because it can be twisted. Those groups, depending on the nature, they're going to withdraw the pi electron density, or they're going to increase the mobility. Carboxylic groups, because oxygen is a withdrawal element, they are going to attract the electron density nearby the carboxylic group or near the oxygen functionalities. So this will leave less pi electron density to move freely around, which is the origin of the electrical conductivity. If you put some nitrogen, and you can play some nitrogen moieties, you can play with the lone pair of the nitrogen, and sometimes that can improve. So when you functionalize, in most of the cases, you're going to penalize the electrical conductivity. The issue is how much are you willing to sacrifice in order to get the functional groups that can also give you another input. In electrocatalysis, for instance, it's very interesting to have hydroxyl groups because you can play with pH and they can also give you an extra pseudo-capacitive effect sometimes. But you cannot decorate your current material with a very high density of OH because otherwise you will lose in the electrical conductivity, meaning that you will lose the intensity of the signal that you want to record.
Okay, thank you very much.
Thank you.
Okay, let me introduce next invite speaker, Dr. Romy Edlinger. She is a junior group leader at TU Munich, and she obtained her PhD in 2020 at the University of Augsburg in Germany, and she was a postdoctoral research fellow at the University of St. Andrews at UK. And you ready? She's dedicated to the uniting like-minded researchers across Europe. This is very interesting. And supporting young research to let their passion for science grow. So today she's going to talk about. Okay, so it's your time. Yeah, please give a big hand.
Thank you. Thank you very much. Perfect. Thank you very much for the kind introduction and giving me the chance to present here today. I will start slightly differently, inspired by a wonderful presentation yesterday by you, Catherine. Very nice. Showing a bit of my trajectory and that sometimes it might look like it's a straight way, but actually maybe it's not. And that maybe trusting in the process itself sometimes is not enough because we have to make it our process. So we're part of this, so make sure you use your chance to make the trajectory yours. So in mine, I didn't actually study chemistry, but material science. So I started off with a different track at the University of Augsburg, and there I got to know metal organic frameworks, where I worked with drug delivery systems and highly toxic arsenic compounds. And from there on, I moved to a postdoc position in St. Andrews, where I worked with Russell Morris and broadened the field of porous materials to include activated carbons as well and zeolite materials. So still having had fun with those types of materials, I decided that I want to stay in academia and definitely come back to Germany and to try my luck there. And I started a position in Munich, where now I have my little research group, and Sylvia here joined me here joining this conference. Because as a matter of fact, also you mentioned it in your previous talk, interestingly, I have 3 PhD students, all of them are female. So we are 100% female. And so in this group, or our focus now is slightly different. Here's the slide that you were hoping for, sorry. We're working on resource recovery and the treatment of water using porous composite materials. So that is very broad topic, because actually if we look at the cycle of water, what we have to keep in mind is that this is the part of the water cycle we all know. There is rain, evaporation, rain again. So this is the normal part. But actually, we have a big impact on that. Because if we look at it a bit more in detail, we see that if we harvest this water, this actually starts containing a lot of materials, more and more emerging materials. Buzzwords like PFAS may have been heard before. So we actively contribute to the pollution of that water, depending on what point in this water cycle we are. I think this one's not, yeah, it's not gonna work on this. So if we're behind industry parts, we have maybe a bit more heavy metals. Or if we're after sewage plants, there can be more nutrition, viruses inside the water. So we really have to be very careful when talking about water, because one type of water is not exactly the same as the other type of water. So what can we do about it? We just heard, actually we can use a filtration material. Very often that will be something like activated carbons, because the idea of these porous filter materials is that it has to be very simple, it has to be scalable, and ideally environmentally friendly and need very, very little energy. So very important for that material then, of course, is we should be highly selective if we want to make use of that material, that we either have a contamination that we take out from the water or a resource that we want to keep after. Of course, easy handling and simple and fast recycling is very important as well. And everything lies in the money, so it has to be cheap. You also highlighted how cheap activated carbons can be. And this, especially for our materials, metal organic frameworks, still is a challenge. So if we look at the status quo, very often what we see is that activated carbon, silica-based materials, or zeolites, they are heavily used. One thing that they do not really offer is that they are not really highly selective, and typically then they cannot be recycled very well. So this is something where if we try to have emerging filter materials, such as metal organic frameworks or materials based on metal organic frameworks, we may have a chance that actually we have a good selectivity in there. So, but I said already, there's different types of water, but also there's different things we may want to do with this type of water. Either we want very pure water in the end that we can drink, so we have to make sure that everything is out of that water, that we don't have any pollutants in there still, or we make use of the yield, something that we can gain from the water. And as most of you may be aware of, metal organic frameworks are very versatile. So both of these extremes can actually be tackled using metal organic frameworks. And there have been promising results showing that we can remove PFAS using metal organic frameworks from water. Also, there has this very fancy work from Wendy Queen that we can use MOFs to extract gold from water. So it's two very big extremes, but actually metal organic frameworks seem to work out very nicely. I think I don't have to say a lot about what actually metal organic frameworks are. Nonetheless, I have this classical slide that we can design the core, we can design the framework, and that is where we have actually the big win. It's a very versatile material class, and now with a Nobel Prize. So this is very, very promising that we can actually address all these issues. Yet, we are not really addressing them. So what is the problem? And that is something where I try to be a bit more critical. So if we look at it, we did a survey and asked a lot of people out there, what do you think, where is the problem? And I think one of the biggest ones is that we don't have very good connections between academia and industry. Typically, the materials are relatively expensive and not really scalable. So open challenges that we have to address is that we have to make these syntheses greener so we can actually scale them up. We have to be sure that we can make them into an application relevant shape, because as a loose powder, it may be a bit complicated to use. And also we have to make sure that by that, we can then actually have a breakthrough to actually use them in an application. But how do we do this? So I think we could maybe go from the idea of something to the realization by critically looking into the field again. Here I have the number of more than 100,000 structures. Yesterday, Susunu said something about more than 130,000. So it is many, many structures out there, so it's a bit chaotic. So we have to be very selective and maybe try to find those materials that are most promising and have maybe the best the best properties that are useful for either contamination attraction, so direct absorption of a contaminant like PFAS, or the resource recovery and enrichment inside the structure. Then we have to shape them. Ideally, we have an iterative process to look into detail. Was this successful? Where is the direction we really need to go? And then in the end, hopefully you can have the resources as well as clean water and win two things at once. This looks very straightforward. At the end of the day, though, I think it is a very complex project and we have to have a very holistic approach and contain many, many things. So we have to start on a very small level. We have to have the microscopic level where we look into materials chemistry. We make those materials ideally in a way that they can address the problem, that they are very specified for the adsorption mechanism that they have to have in the end. Then we have to process them and we have to have a shape that we can actually apply. So now this is more into engineering direction. And also we have to have the global level and look at, is this really ecologically valuable, or can we not maximize the value of the material because we actually cannot recycle them? So this is a very complex thing and needs a lot of different types of expertise, and very nicely put yesterday as well, empowerment and contains we. So I cannot do this by myself, definitely. We need more than one person to do this. So I have my little team and also a lot of collaborators who help out with their expertise in various different aspects. So how do we get started? How do we get there? So first of all, we want to do synthesis. So in the synthesis aspect, we want to be green. So make sure that we only design, use, or produce materials that do not degrade in a problematic way, and also that use very little energy. So best of that would be green in a way that we have room temperature, we work in water, and then we have short reaction times. Typically, though, when we look into metal organic frameworks, we rather find something like high temperatures, organic solvents, multiple days, and especially valid for those materials based on the zirconium oxoclusters, which are highly stable in water, but their synthesis is not exactly the perfect conditions for green synthesis. So what the project of Aya is, one of my PhD students is looking into how can we make them in a two-step process. We start with the OXO cluster and then form various frameworks from that OXO cluster so that we actually can do a green synthesis for those materials. And that you can do with various different types of linkers. Because when we have different types of linkers, we end up with a different topology, and then we have a different option for selective adsorption. We can make use of the versatility of metal organic frameworks by being a bit more crazy and not just change the linker, but also try to play a bit around with the OXO cluster that we're using. So one part that she is doing is trying to include various different metals in that OXO cluster so that we can fine tune the Lewis acidity of the OXO cluster and thereby have even more selective material properties. So this is the start of making the material, but we have to keep in mind we want to go big. So what we want to do is we want to treat a lot of water. So we cannot be okay with just a lab scale of a few milligrams. We have to be sure that we surpass this stage. We have a pilot plant in Garching, so we need a couple of kilograms for this pilot scale, and then eventually we need to go into the ton scale. So one of the things that we're trying is make very boring and simple procedures, but they should be very robust to make sure that we can actually repeat them and have a huge yield in a lot of material. And also one thing, looking at that, we pump a lot of water through this. So these materials have to be highly stable because what we have there is a lot of pressure on the material. So what we do is in collaboration at the DESY, we put our sample in these little Kapton tubes and cycle them in water, put high pressure and release the pressure and see whether or not the material changes. And luckily, up to the pressures that we may need in those systems, they do not change. So they stay crystalline, which is very promising that they actually may do their job when we apply them. But not only being stable is what we need, they also have to be functional. So for that, we look into the adsorption of specific pollutants. In this case here now, it would be the adsorption of different types of PFAS. PFAS are very versatile, very different lengths and shapes. And in the middle part, you see UI-66, which has shown already in Munich that we can adsorb that nicely. However, if we change the water matrix, this I mentioned before, that can be very different. We need something that is more stable, that always absorbs everything. And if you look into detail on the right-hand side, see that NU1000 actually performs perfectly and absorbs every different type of PFAS in various different water matrices. And with computational chemists, we try to understand a bit why is that, why is this so promising and stabilizes the PFAS. You can, no, I cannot point out the PFAS along the linker. So we have an active binding of the head part of the PFAS, and the chain is then stabilized with the linker. So here, very good promising first results, how we can exploit the versatile material class for adsorption of something as complicated as PFAS, even if we go down to the shorter ones. So I mentioned before, we don't only have powders, we have to make sure that we can work with them in a actually handleable, processable, relevant shape. So this is the project that Sylvia is working on. So if you're interested to find out more how we combine the MOF powders with various different polymers, I can recommend to find Sylvia. She knows all about this and is the expert because this is what she focuses on in her PhD and what she will talk about on Friday in her presentation. Of course, you can ask me too. So shaping them will be very useful so that we can have a combination of MOF and polymer in various different geometries. But also, we want to embed more functionalities. So the project of another PhD student, Teresa, is that she combines them with magnetic nanoparticles so that we can have an easier process how we can isolate them if we work only with the powders. And very important here for me is that we sometimes also show things that don't work out nicely. So this is the idea. We start here, we make coarser nanoparticles and everything works fine. Well, actually, there's a lot of syntheses that are done and don't really work out in the first way. So luckily, she managed to surpass the dead zone of optimization and found conditions that actually allow to absorb the core shell materials so that we can have a magnetic isolation of those core shell nanoparticles and do the active adsorption with the MOF shell. And then we have an option to quickly isolate the material afterwards. And various things show us that it works nicely. We do have a proper shell, and then this can be used for the adsorption of pollutants. However, if we do that, very important, I've mentioned there are many, many different MOF structures. And also there is various different types of pollutions. So how do we know how we combine them? This is very tedious if you try each combination. So we teamed up with a startup and they have a non-target high throughput screening. So what we do now is give them various different types of MOFs with various different types of functionalities. And then they cross-check with various different 327 environmentally relevant compounds And we see whether or not or which correlation we can find between the different pollutants as well as the different MOF structures, because this will speed up a lot how many of those we actually test in the lab, because it can be a full PhD probably to just check one component. So that's why we said, let's try this high throughput way and hopefully then speed up the process by quite a bit. And once we have first promising results, we then can take these into this cross-flow ultrafiltration module we have at the lab, so that we then fit our MOF inside here, run polluted water, and then selectively absorb inside the MOF structure. So then we save ourselves a lot of time and can prove whether or not this cross-correlation we have found actually provides what we wanted to do. But I have mentioned before, it has to be a holistic aspect. We have to outperform something like activated carbons, which is super cheap in the end. So how do we do this? How do we look critically into this? Well, for this, we have to do something called life cycle assessment. The standard thing you should do in a life cycle assessment is look at the raw materials you have, the synthesis you do, how you activate the material, and ideally how you use the material. But what we have to keep in mind and often forget is a lot of energy goes into this, a lot of material that we maybe have as excess material, and then in the end, we dispose of it. So ideally, we should close those loops to make sure that we maximize the value of whatever goes into the synthesis so that we don't lose that. Because if we lose it, this is what makes MOFs very, very expensive. And we could maximize their value if we can use them multiple times. So doing this life cycle assessment, this is what I was working on. We found that actually the oxoclusters is, well, maybe a little surprise, the most expensive part of the MOF synthesis. So what she now did is try to look into, is it possible to start from a ready-made MOF, say the end of life is reached, it's dead. We on purpose kill the MOF and decompose of it and then resynthesize it to make sure we stay in the loop and we don't ever lose what material we have, but we can actually make use of that entire material all the time, even though the material degrades a bit. So with this, I'll come close to a summary. I would hope that I think I don't have to convince you that the Lego-like design of MOFs is very useful, that we can fine-tune the selective adsorption properties and then in the end recycle those materials. And here you can see my three ladies and myself in the chair of Roland Fischer and TUM. And what you can see here is that I believe what you need is a good network and a lot of strategies how you can make the we in empowerment actually very, very effective. And for that, I have a few little outlook take-home messages. I think it's very important that you always do like what you do, because then you do it best. Never be too shy to ask for help or critical feedback. That's very important. And keep trying, even though you fail. You have seen this dead zone of optimization. You may encounter a lot of non-successful synthesis, but it will be fine in the end. You'll find the right one. And well, be patient. Not exactly one of my strengths, but it helps to try. And then, yeah, try to build a network, because a network is what's going to help you or support you in the moments that you're down and don't believe in yourself. And for that, I have a shout out, because we do have a very big network, which is called EU for MOFs. It's based mainly in Europe, but it's open to have contributions from across the globe. And if you want to be part of this network or would like to find more like-minded people working in the field, reach out to me. There's also a lot of funding options. We can clarify the details, how it works for each and every one of you. But please make sure that you reach out if you're interested or want to become part of this, because the network is still running for two more years. So if you're interested, reach out. Thank you very much.
Thank you, Romy. Very nice talk. I have a question about the cation exchange or the mixed cation MOFs, because especially regarding the titanium, there's a bit of a controversy whether it actually is integrated into the clusters or rather grafted on the zirconium nodes. Can you comment on, well, whether you have a strategy of verifying it?
So what we do is we start with the synthesis of the oxocluster only. So it's not a post-synthetic inclusion, but they are present during the synthesis. And so the idea was for the zirconium-hafnium mixture, stoichiometric ratios for the formation of the oxocluster will yield the stoichiometric equivalent. Works out perfectly. Well, little surprise, titanium is much smaller than zirconium. It doesn't really want to be in the oxocluster. So if we work with the same protocol and use stoichiometric ratios, we don't manage to include one-to-one ratios that we had planned. but usually it's underestimated titanium in there. And I would say stable formation now in this graph is the idealized world. At the moment, I would say that I'm confident to say that up to this point, we can include 3 to 3. This is still forming nicely and does also form MOFs with that ratio. If you go higher, they start to be too unstable because you cause too much deformation in the oxocluster, and then they don't really want to form. So either we haven't found the perfect conditions yet, or they are not forming.
Sorry, if I may just follow up, because just because you started the cluster synthesis, I don't really see how that necessarily means that the titanium is integrated rather than grafted. Is it single crystal data you're looking at?
Single crystal we don't have yet. Currently, we're trying to solve the structure in electron diffraction. We're getting there because for the oxoclusters themselves, there is no single crystal structure yet. But yeah, I agree. We're trying to tap into every single method and potential to find out if they're actually where they're supposed to be. What I can say is we form the oxoclusters and then the MOFs, and the ratio between what we see in the oxocluster and the MOF is then not changing anymore. So we can stabilize what we have in the clusters. We don't see different phases, we just have the MOF powder. So, but yeah, definitely very difficult to find whether or not they exactly are where they should be. But if you have a good suggestion, happy to hear it, because slowly we are running out of ideas.
Okay, let me introduce next invited speaker, Professor Rie Makiura. She graduated from the University of Tsukuba, and she worked as the researcher at the Frontier Device Research Center of a Seiko Epson Corporation in Nagano. Then she returned to academia as an assistant professor in Kyushu University. Soon after her PhD degree already from Kyushu, she was appointed as a lecturer, then promoted to an associate professor in Osaka Metropolitan University. So today she is going to talk about the meta-organic frame nanosheet, liquid phase interfacial synthesis, and functionalities. So let's welcome the Rie with the big hand.
Thank you, Holly, for your kind introduction. Also, thank you very much for all the organizers for giving me the opportunity to present my work in the wonderful conference. Actually, first I would like to introduce my institute. It's changed. I was actually promoted to the senior professors, and Tohoku University just started in this month. So my institute is now Tohoku University. So I'm like to introduce my work on the meta-organic framework nanosheet, especially the similar to air liquid interfaces. But before that, since I moved to the university, I'd like to introduce my institute, which maybe the most of you might not know. So here is Japan. So the Tohoku University is located in Sendai, here in Tokyo and Osaka, and 1.5 hours from Tokyo by fast train. So there are beautiful campus. So is it good university? Yes, it is. Actually, well, people may consider this ranking for choosing the university. So this is the Times Higher Education university ranking. Is that first one? This is all just selected in Japan. So first one in Tokyo, and the second is Kyoto, and the third one is in Tohoku University. Actually, in different conditions for evaluating university. This is slightly different for the world university ranking and Japanese university ranking. This focuses more on the industrial contribution, which is Tohoku University becomes top. Actually, this top is remained for the recent 4 years. So, and also I'd like to introduce the new program. It's called International Research Excellence. This is the first university. Tohoku was selected as the first university or this the International Research Excellence. What is this? So government decided to put huge fundings in the selected university in Japan. So this advertisement started in last year, and then 10 major universities in Japan applied, and 3 universities, Tokyo and Kyoto and Tohoku, were invited for the interview. And then Tohoku has actually got it for the from the first. You can see that is how big the funding is for the continuing for 5 hours. I mean, you can see as a title, International Research Excellence. This is really, we wanted to have a world excellent researchers, especially focusing on the young researchers and also the female researchers, which is really minority in Japan. So if you are interested in look at the webpage, also that seriously, if you want to work in Japan, please contact me with this webpage, get the information. So my work is frameworks and also other porous materials. And typically the MOFs and other materials are obtained at a polycrystalline state under the superthermal condition. But what we have been aiming is to create nanosheet state, because nanosheets are ultimately thin functional materials. So, and once you get the freestanding nanosheet, you can transfer various different types of substrate. For example, it can be the you transfer the porous substrate, can be the ideal separation membrane. Also, it can be the simple devices. And my work is both related and the MOS and the 2D materials, which is the graphene representative. Actually, I was very happy to have the opportunity to attend the conference with the Nobel Prize winner with Susumu and Konstantin. With this is just last month. It's got kind of continuous, very nice opportunity. So glad to share with this my happiness. And actually, going back to 2007, I started working more thin films. So that time, I was really focusing on them making the thin film rather than nanosheet. And then I discovered that electric interfacial synthesis is really strong method to create a nanosheet. And since then, for the first time, I reported this nanosheet creation of MOF in 2010. And I just picking up the methodology only for the interfacial synthesis technique, not like other techniques like exfoliation. So the top one is like various different, not only the Agumio method I just developed, on the other interfacial, more simple one, and the liquid interfacial techniques or service participation. And the bottom one is like a development functionality with the beginning for the redox active and hopping charge carrier, and also the this red circle is my group. We reported very high conductive nanosheets. So today, from all these topics that I'd like to introduce 2 topics. One is MOF and HOF. HOF is hydrogen bonded organic frameworks for nanosheet using the air liquid interfacial synthesis. And second one is more functionality with nanosheet for the interfacial solar vapor generation. So let me start with the first topic. So how we are able to get the nanosheet with layer interface? This technique is really simple. Once you prepare this shell container with filling with pure water, and we spread ligand solution, which is the porphyrin with peripheral carboxylic acid in this case. Then after that, we inject the source of metal ion into the surface. So this is the experimental setup that you can see the nice pale blue colors, kappa divariant ions are gradually dispersed into 4 troughs. So then the formation of the crystalline MOF nanosheet followed by the synchrotron XRD. It's in ASRA, which is wonderful setup for the electric interfacial techniques, in situ measurement at the liquid interface. So before injecting the metal ion, but it already has a ligand at the electric interfaces, there are no signals. But after injecting the metal ion, now we clearly see the sharp peaks. So we get crystalline something. So because we could assign all the peaks, like HK0, you can obtain the crystalline structure, which is what we expected, that all porphyrin are connected by copper dimers. So, and also I would like to stress that all index are HK0, which means that this nanosheet is perfectly uniaxially oriented. So the nanosheet two-dimensional is parallel to the water surface. And also we observe the surface morphology with a direct measurement observation using Brewster microscopy, that we can see the uniform nanosheet. This is because it's very difficult to see the nanosheet. On purpose, we just left some like a pure water surface, but you can see the whole surface is covered by nanosheet. So, and with this technique, we can get various different types of nanosheets, including the conductive nanosheet using the polyphenylene ligand with peripheral amino groups. It's basically the same techniques. And we can also confirm the crystalline structure with high resolution TM observation. And then when we tested the conductivity of this nanosheet, it actually recorded as highest conductivity in the polyphenylene MOF nanosheet at that time. So which is like a nanosheet means that less than the thickness less than 100 nanometers. And also this technique is not restricted to the MOF. We can get different types of porous materials. So I'd like to also introduce hydrogen on the organic landmarks. And so now, because we're not talking about MOF, so we don't need metal ion, only the organic molecules. So we selected the building block as it's called BTB with triangular molecule with carboxylic acid. So since we are not using the metal ion, so we just prepared pure water as in the shallow container and just put the ligand solution on the surface. And it just self-assembling manner, surprisingly nicely forming this porous network. So this porous network was confirmed with, again, the in situ X-ray measurement with the red one. And after transferring solid substrate with silicon, the crystalline remains, that we can see the same patterns observed. And also in this case, at the liquid interfaces, we could see the single peak at the out of plane stoichiometry, which is you can get the information with the direction of the vertical to the liquid surface, which means that stacking structure is formed in this sense. So the nanosheet thickness is about 10 nanometer. So it means that considering the Piper stacking, about 26 layers are stacked at the air liquid interface in the self-assembling manners. So, and interestingly, and this molecule is well known for many MOF construction ligand. And this molecule itself, there are no reports on the bulk crystalline structure. So we get a single crystal by ourselves, and we try to solve the crystal structure with a single crystal X-ray analysis. And interestingly, this molecules form the hexagonal networks. How the potential there porosity. However, in the bulk crystal, this really complicated interdigit structures form, which is kind of sacrifice the porosity, which often happen the porous material because this complete porosity is not stable. So while applying the air liquid interfaces, we are able to get a porous oriented nanosheet because of the interface is strictly restricted the molecular alignment parallel to the liquid surface. So there are no space for the other molecules interdigited into the frameworks. So in order to prove the porosity of the nanosheet, we measured nitrogen uptake. The black one is the single crystal with the same ligand. And the red one is nanosheet. You can see that even though they are formed from the exactly same molecule, but completely different behavior. Only the nanosheet case that we can see the deep uptake at the low pressure region, which is the evidence for the existence of the pore channels. like we expect from X-ray diffraction structure. And not only the nitrogen uptake, we measure the water vapor uptake and also oxygen uptake. And both cases, it's again that completely different behavior between the bulk crystal and nanosheet. This is sure it's coming from the different crystalline structure, even though they are formed by the identical molecules. So I would like to stress that this electric interfacial techniques is not just solution to get a nanosheet state, but also the promising technique to create the unique structure which you cannot obtain other techniques. For example, like this bulk structure is completely complicated structure. We actually try to different techniques, like to get the films with the drop gas and immersion with both very popular techniques for the solution-based thin film. But it's both cases just get like a bulk-like crystal. We are able to get a thin film with vacuum evaporation, but it looks like very thin, smooth film, but it's not crystalline. So only the application with electric interfacial synthesis, we are able to get the crystalline porous nanosheets. So actually expecting this technique will create further unique techniques with other different molecules. So let me move on the next topic for the interfacial solar vapor generation. So the interfacial solar vapor generation is a modern key technique to make a sewage useful for our life. So the water in sewage is go through the substrate material to the top photothermal material, and the water vapor was condensed and collected with other containers. This is very simple technique, but it's really promising technique. Actually, there are many reports on solar vapor generation with using the MOFs, but all of them are multi-component composite, like together with polymers and porous carbon and other inorganic compounds, but no reports on the single component MOFs. So actually, instead of aiming to improve the efficiency of this technique, actually, I'm rather interested in the more fundamental aspect, which is interaction between the water and the frameworks. So water dynamics, and this is closely related to the evaporation. For such purpose, single component, very simple system is ideal to understanding the phenomena of this system. So if you want to get a single component, so you have to have all necessary conditions with the floating, the thermal insulation, the solar absorption, but actually our MOF with porphyrin network has a quite good candidate. So we have tested for the solar water evaporation, but since we are able to, we could get the nanosheet with our techniques. It's not very difficult to prepare the measurement system. We just put the water container with a surface MOF nanosheet, and then the evaporation was measured with loss of the weight. So this is the radiation of the solar light. So black one is without solar irradiation. The red one is with solar irradiation. Obviously, it works. So it's comparing the water only, so it means that there are nothing on the surface, but with water, the amount of the evaporated water is like more than double compared to the water only. So the one reason is that efficiently the surface with of the surface was existing the MOF nanosheet was heat locally. This is really helping the water evaporation. And also the since as I already said that I'm interested in the more fundamental aspect. What is the interaction between the water and the frameworks? So there are many reports on the special water conditions in the confined nanospace, like nanotube, also the MOF cases. But there are like static water condition. Well, what I'm interested in is dynamic behavior of the water, which is directly influenced to the evaporation. So there are no dynamics of the MOF with water in MOF, but interesting paper showing that this is all polymers. But this intermediate water is even like easily vaporized compared to the free water. To get the hint from this report, I was tested for the various measurement. To first confirm the porosity, our MOS indeed has porosity with nitrogen absorption networks. For the structure, we know that there are pore in the 2D network, also between the networks. And from the some gravity measurement, you can see that here is this nanosheet was soaked into the water with a lot of water contained. So here is the steep loss of the weight, which is, and at a very low temperature, which is much lower than the water, the boiling point. So in this term, so why? So to get some understanding, we also conducted a water vapor absorption. The blue one is just ligand, but the red one is more. Actually, opposite behavior from nitrogen absorption. The water is not really absorbed into the water. I think this is the key that since the water molecules are not strongly trapped into the phloemax, it can go through to the pore, but can be easily evaporated at the interfaces. So this is a summary. I introduced two topics: how we get the nanosheet at the liquid interfacial technique, and also the vaporization using the solar light, using the MOF nanosheets. Finally, if I have a bit of time, so I'd like to introduce finally, I'd like to acknowledge all my group and also collaborator and the fundings. Also, since we are like we might focusing off, I just introduce, I have two children, like 12 and 7, they're not very happy that I came here alone, but okay, maybe next time we come together. And then also the Hori was organizing the round table in the Merida that for the editors forum. So I'd like to introduce my editor job. I'm an editor of Applied Surface Science, published by the Elsevier. So this journal is actually published in 1985, so 40 years history, quite old. And impact factor, okay, not bad. And actually, we get like 16,000 submissions per last year. It's huge. And we have 38 editors. And actually, the good thing is that 90% of all articles are cited. So not bad. So, and we are organizing our journal organizing the international conference every 2 years. So next year we'll have a conference in China. If you're interested, please look at the webpage, and the submission deadline is actually next month. Okay, thank you for your kind attention.
Dramatic difference. Do you have a rationale on the molecular level of what guides that? Is it for accessibility?
Yeah, actually, I was thinking because the nanosheet doesn't get so much water, while the bulk one is sharp uptake. And I was thinking because bulk, there are some edge of the carboxylic acid, the phloemax is not completed. So this carboxylic acid, this polar part was kind of attracted to the water molecule, while the nanosheet cases was kind of pure, all of them are formed the porous network, and all carboxylic acid are connected using for the connection, which is the porous inner part is hydrophobic. That's why they don't really attract the water itself. This is my understanding. Thank you. Thank you very much.
Okay, so we will have a 2 oral presentation from now. So, okay. So next speaker is Adriana Jalanska-Badinska from Poland. Today, she is going to talk about copper modulated PCN222 for photocatalyst, right? So. Ready? Okay.
Ready, and how to switch the. Oh. Okay. Okay, so good morning, ladies and gentlemen. It's a great honor and pleasure to be here. And for this short talk, I choose, the only small part of our work, and my major is in heterogeneous photocatalysis. So for this reason, I decided to talk about the PCN222 modified by copper and applied for the carbon dioxide photoconversion. So as you know, carbon dioxide belongs to the greenhouse gases, and it's emitted in millions of tons into the atmosphere per year. So in European Union, according to some directives and rules, we are obligated to drastically reduce of the carbon dioxide emission in the upcoming years. And I think that it's the main reason of development or just accelerating development of different technologies which are able to reduce carbon dioxide emission into the atmosphere. And one of the possible technology is also heterogeneous photocatalysis. And as you know, because in the plenary lecture, we are introduced into heterogeneous photocatalysis. Using heterogeneous photocatalysis, we are able to convert carbon dioxide into the different hydrocarbons, and in the presence of the solid photocatalyst and UV or visible irradiation. And the final product is depend on the band gap structure of the photocatalytic materials. So it means that the conduction band of the photocatalyst should be more negative than the reduction potential of carbon dioxide into the desired product. So still among different photocatalytic application, I think that carbon dioxide photoconversion has the lowest efficiency, and this technology have the lowest TRL level among other photocatalytic application. And for the so many years, different semiconductor materials have been mostly tested, but recently also the MOFs start to be employed for the photocatalytic conversion of carbon dioxide. And in this huge family of MOFs, some of them also possess photocatalytic activity, and moreover, some of them are enough stable even under UV and visible irradiation, but also they are enough stable in the reaction environment. So for our research, we decided to use PCN 222 just due to the narrow optical gap, and also due to the position of the luma of this MOF. So the main scope of this work was to enhance PCN-222 efficiency toward carbon dioxide conversion into the formic acid by modification using the copper. And in our work, we decided to use post-synthetic metallation, also just to decrease the cost of the modification of the MOF. And we decided also to test how the amount of copper used for the modification affected surface properties of this MOF, photocatalytic activity, and how finally it affects the mechanism of carbon dioxide photoconversion into the formic acid. Why we decided to choose the copper among different possible metals? The first reason is that the copper presence should suppress recombination of photogenerated electrons and holes, and it's beneficial from the photocatalytic point of view. And additionally, we expect that introducing of copper ions during the modification could result in formation of copper oxides, and finally we are able to form heterojunction, and it's also beneficial from the photocatalytic point of view. So in the first step, we just synthesized PCN-222 using well-described solvothermal method in the literature, and after separation, purification and drying of this material, this MOF was redispersed in organic solvent in the presence of different amount of copper ions. And after heating, obtained material have been also purifying, drying, and finally used for further investigation. So we used the huge excess of copper amount in relation to the zirconium, which is in the MOF, and the molar ratio of copper to the zirconium atoms varied from 3 up to almost 25. So finally, all obtained samples have been characterized using the wide spectrum of different techniques. And firstly, we would like to confirm that really we have still the MOF structure, but the most important was to understand what is the chemical character of the copper which was introduced into this structure. So the structure of the MOF was confirmed using both XRD and also TM and SEM analysis, but TM analysis and also SEM analysis also revealed that we have some additional agglomerates which are formed at the surface of the MOF. And EDX analysis just revealed that copper distribution is quite homogeneous at the surface of the MOF. So you have to believe even it's not quite visible here. And moreover, we observe much higher concentration of the copper in the place of these agglomerates. And XRD analysis also confirmed that we have two types of copper oxide have been formed, so even copper 1 and copper 2 oxide. So to understand how copper was introduced into the structure of this MOF, we also used XPS and other techniques. And finally, we assumed that during this post-synthetic modification, in the first step, copper is binded by the porphyrin ring. And after metallization of this porphyrin ring, the excess amount of copper ions are adsorbed at the surface of the MOF, and finally we observe formation of both copper oxides, and the depending on the amount of the copper ions introduced during the modification step, we observed that copper 1 oxide or copper 2 oxide was predominant in different types of samples. So finally, also we investigate all obtained materials towards sorption properties. So we observed that both BET surface area and adsorption capacity towards carbon dioxide decrease with the increase of the copper ions used for the modification of these materials. And also thinking from the photocatalytic point of view, it's important to create materials which after excitation are able to utilize electron and holes for the different reaction pathways. So we try to suppress this recombination of photo-excited electrons and holes. And to investigate, we used photoluminescence and time-resolved photoluminescence spectroscopy. And what we found that generally modification of PCN 222 by copper suppress this photoluminescence of the samples. So it means that we are able to suppress recombination of photo-excited electrons and holes. And one samples which was prepared with the generally medium amount of copper possess both the lowest photoluminescence and the most extended lifetime of photogenerated electrons and holes. So we assumed that this sample should possess the highest photoactivity in carbon dioxide photoconversion. So finally, we checked the photoactivity of, sorry, I don't know, it's my fault or not. So I don't know how to come back to the, but I can continue maybe. So we check photoactivity in carbon dioxide photoconversion, and we observed that in all cases, these samples are active under both UV and visible light. And we also observed that the main product, okay, so it's going without me, but I can come back probably. Okay, thank you. So we observed that the formic acid and carbon monoxide are the main products formed after carbon dioxide photoconversion under visible light. And these samples which possess the best properties, luminescence properties, also possess the highest photoactivity in formic acid formation. And generally the amount of formic acid formation for these samples was about five times higher than in the case of the pristine PCN 222. So this samples also was selected for the further investigation. So we checked that this sample still is active under more visible light. So if we use for irradiation wavelength longer than 455, we still observe formation of the formic acid. And we also checked that this sample is stable in 5 subsequent cycles of the photoreaction, and the amount of the formed formic acid is generally stable. Also, just to be sure that the observed product, that observed formic acid was really resulted from the carbon dioxide photoconversion, we proceed experiment, which was for which we used the isotopic label at carbon dioxide, and we confirmed that in the product, in the formic acid, we have this carbon 13. So really, we are sure that the product not originated from some impurities which are present at the surface of the MOF. So we try also to compare our results with the results from the literature, but it is not so easy because generally in the heterogeneous photocatalysis in different works, people use different conditions and different irradiation sources. But we found that these samples which are modified using this post-synthetic copper modification is generally much more active than other samples of PCN which are modified using also copper modification. So finally, based on the DFT analysis, we try to understand how this kind of materials are excited and what is the mechanism of the heterogeneous photocatalytic transformation or carbon dioxide. And based on the calculated position of the conduction band of both copper oxides and LUMO and HOMO of the PCN 222, we assume that all these components are excited by visible light, and after excitation, holes
again several times, 3 times. In the end, copper structure has completely changed. For the rhodium case, they keep their crystallinity and the structure. I thought probably because of the structure of flexibility depends on the matter. Then we can change the kinetics of the under the light irradiation. So this is the take-home message. I successfully synthesized the new work. I think I also really recommend you use the MOP. Also, you can choose the different shape of the MOP, not only cuboctahedron. So also now still we need to study the photoisomerization kinetics because there is not so many paper. So we have to figure out what is the important to change it, their kinetics in the structure. Yes. So this is the almost end of my presentation. I really appreciate the Stepan Cascade group, especially Professor Stepan and my group leader is Volodymyr, and then Irena also my colleague, and then all the collaborator. Especially actually this Pandi Maria Reine postdoctoral fellowship is the support for the woman scientists. So I think this is quite perfect funding in this time. Also, if you are interested, my paper, please check the website. And then quite recently, I also make my homepage. So if you are interested, please visit us. Also, this the another things. Next year in Dresden, we have international symposium on the characterization of porous solid. Especially, I'm organizing committee of young investigator forum. So if you are interested, please join. And then the abstract deadline is actually still we have a lot of time to think about. So please join. And then the really last the slide. When I prepared my presentation, I also I remind my research, the academic career. So when I start my bachelor, actually in the chemistry department, the women and men's ratio is almost same or over higher. So, and then we graduate, some people go to the industry, and then some people also study more. So in our group, the master and when I had a master and PhD, in our group, also the men and woman ratio was almost the same. And then now I'm the postdoc, the status. So many my former colleagues, especially women scientists, also are also still keep their career stages. So I thought, why? Actually, this is a very huge change compared with to the compared to the 10 years ago or 20 years ago. So I thought I have a mentor who are in front of me. So I really motivated when I met the many the women professor and then the leader and senior scientist. So hopefully the student and the postdoc, we keep our academic career, and then next time we will meet again. So yeah, thanks a lot. Yeah, this is my yeah. Thank you very much.
Thank you very much. Because of a time limitation, okay, so let me move on to the next speaker. Sorry. Excuse me. Sorry. Okay, so let's move on to the next speaker. We have a very special speaker, okay, Sandra Malagon. So, okay. So Sandra Malagon holds a PhD in philosophy of science from UNAM, and she's the researcher in AI governance. Her work focused on the collaborative, the evaluation of a language model, the study of a computer infra in the global south. And she is a director of Keras, Con Impacto. Okay, so today, okay, she's talking about the gender equality, equity, and diversity in science, maybe related in AI. Okay, so let's welcome and please.
Thank you so much. Thank you for the presentation and for the invitation to this talk. So I will start. Oh. Oh, okay. Oh, okay, perfect. Thank you. Well, I want to start to talk about what we mean with bias in AI. And well, bias is not only a technical flaw. AI system reproduce pattern of inequity, and these patterns became normalized as neutral or objective. Sorry. And it's very important to understand that it's like a cross between the technical risk, but also the social bias that came of how the models are created, trained, and deployed in different contexts. So I will start to talk about some examples of research that shows how this could be this bias. Well, in this study for 2023, they try to understand if a large language model was like culture, where is more close to. So this shows how close or far are different cultures one of other. And as we can see, GPT in this case This trial was with GPT 3.5 and GPT 4. It's so much more close to cultures like Germany, New Zealand, and basically the global north, countries with a high level of economic development, but it's more far away of cultures with are not in these specific conditions. We can see like it's so far away from cultures in Asia and in Africa. But also maybe we could think that in Latin America, as we are so close to, for example, United States or Canada, maybe we could stay more close, but it's not the reality. There are more close, like some small countries in Europe or some developing countries in Asia, like South Korea. Okay, with this study, we know like big AI models have like moral line with certain values and with certain cultures. But what this mean in practical stuffs? So another study, this is from 2025, they want to understand how the surnames could affect the responses that make several artificial intelligence. So basically they have four kind of surnames. Legacy surnames, like people with wealthy from far away. Legacy variants, that is like similar surnames, but not exactly the same. Also rich surnames, like people that is very wealthy in this moment. Rich variants and common variants, that it's all these surnames that don't belong to rich or legacy surnames. And also they want to compare between different countries and languages. So they measure this in with Thailand and US. Some of the results is like, for example, in perceived wealth, the models have significant differences between legacy surnames, rich surnames, and common variants. Well, the models are able to perceive like encoded social economic variants, but sorry. Sorry, but what is but this is not used that they are able to recognize. They see patterns related, for example, with another characteristics, for example, perceived intelligence. So in this same study, they see that when in the experiment, when they measure the perceived intelligence by the models for with characteristics in the different kind of surnames for Thailand and for USA, these significant differences they're still there. And it's also curious because in US, it's able to separate legacy surnames from legacy variants. Now we have like information about they have a bias related with how they were trained, related with surnames, and also how this is related with specific characteristics of people. But this is particularly concerned because this is not how evaluate a person. It's how evaluate the opportunities or a space where these people fit. And in the results, they show that, for example, for entry higher or political careers, the models have also differences between perceived power, health, perceived intelligence, and commonality are related with how they measure the probability to be higher in an entry level, or how, or the probability that they recommend a political career for depending of the different previous measures. Why this is important? Because artificial intelligence now it's in every space of our common life. They are pretty used in this moment for recruiting for companies, but also there are started using and will be so much more common in the future. Get them to review applications for education. They will review health insurance, several things pretty related with the opportunities of people to be in certain spaces. So these bias show just in the surname, but they are able to identify differences related where you come from, your language, your gender. So this is pretty concerned because in the next slide, we will see that it's not used from technical bias came from the training, the data. It's also because companies and other actors have certain goals to achieve, and these goals are not in all the cases aligned with different culture contexts and the difference in the world. Okay, so where they came from? There are more like a little bit more technical, like algorithmic bias. They came from the training data, the model architecture, optimization objective, and self-reinforcement patterns during the model updates. Why is not used technical? Because the training data reflect which data is put in the model. The majority of data came from internet, and in internet is more there are a lot of more information, first in English, and the second from north countries. So this is a problem because in the training, the models get these specific cultural bias, as we saw in the previous slide. But there are also instructional or policy bias. For example, reinforcement learning for human feedback. This is chose for the labs, it's not used like something technical. Fine-tuning and preference modeling, policies layers and moderation rules, and pretty important, institutional value choices, because they are trained to optimize certain goals. For example, to get appropriate answers, to be professionals, other goals. And if you are users of the technology, maybe you can see that there are differences between the models from different companies, because different companies have different goals. Some cases that show this are some events, for example, in Grok, the artificial intelligence for XAI. They have like a couple months ago a problem because the model tried to put information about a false genocide in South Africa in practically every conversation with the users. So in Twitter, the user started to put why this model is telling me this, and was because it was an instruction for the lab in the more superficial layers of the training. Was not very successful because contradict the more in the instructions of the model. But this is a case where was very clear that something was happened. But in general, we are not able to know this because the companies intentionally don't make this public. And it's like, there are like some ways to do this with independent experiments, but is not like the same as if the labs will be more open. about these goals and instructions. Okay, but it's not just like in the AI ecosystem, it's not just the goals of the labs, it's related with geopolitics. For example, in this map, we can see the hardware quantity that each country has. As you can see, United States is where they have like the more quantity of hardware. There are in a little bit better position some countries in Europe. Sorry, but this was it's not show, but there are in Japan and certain and South Korea. Sorry, yeah, South Korea. Also, they have like good amount of hardware. Of course, China, but there are a lot of regions that are in gray that we don't have like practically nothing of hardware infrastructure. And in the and we will see why this is really important. But it's not just how much infrastructure you have, is this infrastructure how is the most biggest model that you can train with this infrastructure, because depending on the kind of GPU that you have access and other hardware variables, you could be more able to do biggest models or not. In this case, we can see that the country who have significantly more, it's more able to train a big, largest model, it's clearly United States. In this case, we don't have information about China because it's not public. And we have also a concentration again in Europe and some countries in Asia. But as we can see, a big part of the world, it's empty. By the way, if you are interested in more data about this global AI compute map from Epoch AI is an interactive data set and is pretty interesting with so much more information than this. Okay, so which are the different problems that came from this distribution? Well, the first is that as we saw previously, have this concentration is related with how aligned and in which values there are aligned the artificial intelligence, and have sense that they are more aligned with the countries where are not used with the data used for train them. It's also because the infrastructure and the goals of the companies are also centered in certain spaces. But one of the consequences of this is that if all the infrastructure is concentrated here, the rest of the world, we have less capacity to decide what kind of technology we want and how and in which values we want to be aligned, and also to have certain kind of decisions about how is deployed in our countries, because this concentration don't mean that the artificial intelligence will not be deployed in the rest of the world, but will be deployed from very few countries, and in fact, very few companies, because there are not so many of them able to create this technology. And in the organizations that I work, as I show and Carreras con Impacto, we start to think about, well, this is the current situation, but what we can do from our spaces. And basically, we, with other partners, we identify like some pillars to autonomous AI capacity in the global south. The first one is independent evaluation, to understand how models behave in our language, institution, and cultural context. Why this is important? Because currently several of the information that we have about the model performance came from the labs that create them. So it could be like have bias, and we are not completely sure that it's accurate information. Which is the problem? These experiments are some kind of pretty expensive. They need a lot of compute, but the most important, they need a lot of expertise to do them. And it's also a technology that grows pretty fast. Practically each 4 months, we have like updates or new models. It's exponential growth. And it's pretty difficult to have like updates, evaluations. As you saw, I show evaluation from 2023, and it's 2 models behind of the current model that we are currently using from OpenAI. But also, if you saw, these students came from also for the global north. They are for Harvard and the MIT, and we have pretty few information about this in other contexts like Latin America, Africa, Asia, etc. And particularly in Latin America, except for Brazil, we have like a little bit of well, we are a little bit more represented than minority languages because there are several Spanish speakers, talkers. But for example, in languages like they have less population, or even they have like very different structures, this bias it's worse and worse. So well, we need more independent evaluation, but it's expensive and need a lot of expertise. We need policy and regulation to ensure the deployments align with local public interest and not only with strategic or commercial goals of foreign developers. And the third one is compute and infrastructure to adapt, retain, and govern models. Because without compute, there is not adaptation, and without adaptation, there is not sovereignty. Okay, the problem with compute infrastructure is pretty similar of the evaluation because it's extremely expensive. But we start to think, okay, it's expensive, it's difficult, but what we can do from the global south. The question was, how feasible is this to have independent evaluation, policy, and our own infrastructure? And we, well, as a little context, in Carreras con Impacto, we have a mentoring program in governance of artificial intelligence, and in ISHO, it's more like research. And this year, we have 2 research projects that is some examples that what we can do with less resources. The first one is we create an independent evaluation of 3 different models and we want to identify if these models have difference in performance, resolving mathematical problems at the university level mathematical problems. So the goal of this experiment, the results, was interesting, but the most important was we want to prove 3 different things. One, independent regional evaluation is possible with academic rigor. Collaborative models of practice can scale across institutions, and non-English language evaluation reveal different failure models that English-based benchmarks. So in a 3-day collaborative hackathon, the hackathon was online. The students and researchers from Latin American countries develop and validate a Spanish reasoning dataset. For this dataset, they create 100 novel problems that there are not internet to avoid contamination. And this was translated in, was created originally in Spanish and translated to English. And after that, they evaluate the differences. In this case, the 3 days hackathon was used to create the dataset, and they took like several, like 2 months to finish the the whole evaluation. But what we saw with this related with evaluation, it's possible made it with expert knowledge in collaborative ways and in a very cost-effective way, because this data set costs like at least 10 times less like the cost reports for universities in United States, but also shows that in our countries we have a lot of talent people, a lot of expertise, knowledge, but we need like to align them to be able to create this. So basically our goal was, this is possible, and the answer was yes, it is possible. And in this case we use mathematical reasoning because have like a specific some specification that it's better to create benchmarks, but this could be do in any field. Now we are working in a benchmark for synthetic biology, but this could be in chemistry, in physics, in all the areas. And in fact, in this moment, the big lab techs, they are very interested in hiring people to work in this because they want to test this model in the more high levels of understanding, like PhD, or in the case of maths, now our benchmark focus like in fields medals level. They create like a data set and they test with several models. So this, I think, could be very useful in all the fields that with scientific interest. The second one is related with infrastructure. We decide to try to understand how feasible is train a model in Mexico and Brazil. In this case, was a model similar to DeepSeek V5. In the moment when we start the research, was the same performance but different size of GPT-4. And well, there are like a lot of information about which are the restrictions to develop, to train models. And in some point, several people believe that the more restricting thing was the access to GPUs, because they are only created by NVIDIA, and it's pretty difficult to have from other places. And when US banned to NVIDIA sold GPUs to China, and this is one of the reasons why China is behind to US in this race. Well, we trying to think like the GPUs, and if US restrict this in the global south could be the more impactful thing. And we discovered that in fact it is not. Now the compute in the new GPUs as the V100, it's pretty efficient. So the main constraint is in energy. These models need a lot of electricity to be trained, and not use a lot of energy. They need for at least in all the training at least 6 months, and it's with high peaks. So several of the infrastructure in the world is not available to do this. In fact, now in US, there are like a lot of projects to construct energy infrastructure because they need this to train biggest models. XAI and OpenAI have like big projects. They want to have 10 gigawatts for each model. The current level it's like 100 less powerful. Also, we want to understand, it's like different, several of the discourse related with if it's possible, train models outside to these big hubs is not possible. Be competitive in this race in frontier models. But maybe for the global south, we need usable models, not frontier ones. And in this specific in this specific case, we saw that it's pretty feasible to have a model 1 year behind of the frontier model. And this is not a completely fake. There are like very powerful models, I mean, so much more lower cost. If you want to see the full paper, but we saw that it's economically and feasible and technical train a model like GPT-4 with this capacity, but in a smaller size. It's feasible. Okay. So the conclusion is that there are bias in the artificial intelligence model, but in the global south or countries where we don't have the same level as US and Europe, we can do a lot of cost-effective interventions, and we need to invest in infrastructure, talent, and institutional frameworks. And thank you so much.
Thank you. Because of time limitation, okay, please use at our lunchtime for discussion. Thank you very much. And I'm really, really sorry, I skipped the one speaker. Maybe I was hungry, so please understand my mistake. Last speaker for Flash, presentation is Liliana Ramirez from UNAM. And she's going to talk about MOFs combined with the biopolymers as a sensing substrates. You ready?
Yeah. Thank you. Well, I am a college degree, so it's so important to me present here. I am going to talk about metal organics. It's like a summary, like the Dr. Rumi says a few moments ago. So practically it's summary about that she talked. Okay. As we know, the metal organic frameworks have attracted considered interest due to their high porosity, adduced structure, and strong terminal affinity with specific MOFs, because the structure with metal ions with organic minerals, it's important to us. However, their practice use in sensor may be limited by their stability and mechanical fragility. But on the other hand, the biopolymers are biocompatible and environmentally friendly supports that can establish these structures. The role of biopolymer, such chitosa, alganate, cellulose, are excellent scaffolds for supporting MOFs. According to the review by Rajas 2019, these natural polymers provide flexibly, hydrosafe, and processability, which improves sensors from performance. The incorporation of MOFs into biopolymer matrix improves mechanical stability, resistivity to humidity, and environmental sustainability. The research is hybrid materials, the selective of MOFs, but gains the biodegradability. According the review by the Dr. Orcajada and the college in 2018, the MOFs can be adapted for gas capture, separation, and detection, offering super areas and selectivity. This characteristic enable molecular recognitions of analytic as toxic gases as ammonia, carbon dioxide, methane, and the synergy between MOFs and biopolymers creates multiple platforms for gas sensitive. So the such hybrids exhibit insights, signal transduction, selectivity, and reusability. The high-gates strategies like functionation MOFs with biopolymers change the target gas capture, the probably important sensing, the device for environmental monitoring. And the last, it's also short this talk, it's the combination of biopolymers and MOFs opens the sustainable way for advanced gasization. This series combines the precision of organic structure with the versatility and environment friendliness of polymer naturals. Thank you.
Yeah. Okay, then let's thanks again, Liliana. Yeah, thank you very much. Okay, attendance, and I think this is the lunch time. Maybe announcement from. No, okay. It's just we can have a lunch. Okay, so we will start from 1:40. 40. Yes. Okay, please enjoy your lunch. Thank you very much. Yeah, 1:40. We have a plenty time. Enjoy.
Good afternoon. Welcome back to everybody. Before we start this afternoon session, I was told that we are going to try to get a photo of everybody right now. So I think that we will follow the instructions of the person in charge of taking the picture, but if you want to move on over here, all of us. So after the photo call, it's time to go back to business. And it is my pleasure to introduce our first speaker of this afternoon, which is Miranda Marinescu. Just a brief introduction before I leave her the floor for the presentation. Dr. Marinescu is an associate professor at the University of Southern Carolina, and her work focuses on designing, synthesizing, and understanding novel catalytic system essential to the development of efficient solar-to-fuel technologies. She has been recognized with several awards and fellowship, and I will just mention some of them, such as the NSF Career in 2016, Rising Star Award in 2018, and the ACS Harry Gray Award for creative working in organic chemistry by a young investigator in 2021. So please welcome Professor Marinescu for her presentation.
Hello, everyone. Hello, everyone. Thank you very much for the very nice introduction. I also would like to thank the organizers for the opportunity for inviting me. It's a great honor to be here and tell you about our research. So thank you again for the very kind invitation. So today I would like to tell you about our work at University of Southern California and our work in solar energy conversion. So my group is interested, solar energy is very abundant. However, one problem with the solar light is the intermittency of the sun. We use a lot of energy at night, but sun doesn't shine at night. So what we need to do is we need to develop methods to capture, store, and transport the energy efficiently. With capturing, we're actually doing quite well. And you will see here in the next slide that at least in Southern California, it seems that we have too much solar. In 2024, it was reported that they actually throw away enough energy to power the households of San Francisco for 1 full year. So again, solar energy is very abundant, and what we need to address now is storage and transportation. And so one method is to store this energy in batteries, and that's definitely an application that has been used. But what my group is interested in is to store it in chemical bonds. So we're interested in conversion of abundant small molecules, in particularly water is what I'll be talking about today, but other small molecules as well, like carbon dioxide and other, and convert those into value-added products. We are interested in my group, again, in developing materials for each of these half reactions, water evolution, or CO2 reduction to a variety of carbon-based products. And my group, we're interested in the development of novel catalysts using inspiration from nature and then heterogenizing this molecular catalyst to take advantage of the combined properties of homogeneous and heterogeneous catalysis. And that's where we are interested in using MOFs to heterogenize motifs because MOFs have this homogeneous, heterogeneous nature. And then here I listed, I have, sorry, too many. Here I listed the requirements that we need to take into account when we develop novel system. They need to contain only inexpensive elements. So you will see we'll use a lot of first row transition metals. They need to be stable under the reactions conditions. I'll point out one of the MOFs that we're using, it's stable in aqueous media at pH 1.3, but certain MOFs may not be stable under those acidic media. High catalytic activity, it's important. High selectivity, this is particularly important when you can have multi-products, such as in the case of CO2 reduction or other products. And then longevity, maintaining this high activity and selectivity for a long period of time. And then scalability is important as well. So nature is very active and selective, but it's not scalable. And we are interested in using the same motif as nature uses, such as secondary amines, because they can serve as a proton relay, with the amine being protonated and delivering that proton to this iron hydride to facilitate the hydrogen evolution, and in a similar way, acts to the cysteine residue, also transferring that proton to this bridging hydride. That's what we developed as well in my group. We developed a variety of different projects that are homogeneous and heterogeneous. So there are two projects that we have developed on homogeneous systems. This cobalt macrocycle that contains secondary amines that are important for the activation of CO2. And then this phosphinothioate complex, where again, thiolate can serve as a proton relay as well. And that complex is active for the CO2 conversion to formic acid. We also develop methods to heterogenize motifs. And here we have two projects. One is to use this diazonium reductive coupling and generate materials that are covalently attached to the electrode using this diazonium reductive coupling. And those are very active for CO2 to CO conversion. Or another method, which is maybe more general to heterogenize molecular complexes, is to incorporate them in an extended framework and generate this one-dimensional and two-dimensional polymers. So we've been using with a lot of thiolate motifs, dinucleating and trinucleating motifs, and that allows us to make one-dimensional and two-dimensional motifs. So again, MOFs have a lot of interesting properties. I already mentioned this homogeneous, heterogeneous nature. Site isolation that would limit bimolecular decomposition, which is very common for homogeneous systems. However, if you are interested in using them for electronic applications, they do have one big limitation, which is their low electronic conductivity. So when we started looking at this, then we said we and others in this area have considered using metal complexes that have redox active ligands, such as this dithiolene motifs that can either donate or accept electrons. And these two reports are among the first reports of conductive MOFs, and that was the conductivity that was reported then. And just in the last decade, that number increased by about 8 orders of magnitude. So there has been a huge development in the area of 2D MOFs. So we were particularly interested in this cobalt dithiolene motif that was shown by my postdoctoral advisor, Harry Gray, was well studied by him. And it is well known that there is an extensive delocalization between the metal and the ligand orbitals. So we thought that that is very important for conductivity and then electrochemical activity as well, because the charges are not isolated anymore. So when we started at USC, right before we started, there were these examples in the literature by the Nishihara group, where they reported this nickel benzene hexathiolate coordination polymers that display very high electrical conductivity. And then studies by Mirchadinko using this nickel HITP systems that were again showed high conductivity as well. So, but there were no examples of electrocatalytic MOF. So that's the system that we looked at for hydrogen evolution. And now there are analogous systems, this nickel diimines for water oxygen reduction, metal porphyrin containing MOF for CO2 reduction, ruthenium bipyridine for water oxidation, and many other systems that have been developed just recently. So once again, we were interested in this dithiolene motif because it was shown by Eisenberg in 2011 to serve as a hydrogen evolving catalyst. And then DFT studies by Sharon Hamas-Schiffer suggested that the thiolate moiety is protonated twice. Then there is a hydrogen atom transfer from this thiolate to the metal center to make a cobalt hydride. Those two moieties can now couple and produce hydrogen. So we were interested in developing methods to heterogenize this motif and again, developing one-dimensional and two-dimensional materials. The way we synthesize these two-dimensional materials is through an interfacial reactions where we have the two regions, the ligand and the metal precursor, in two non-miscible solvents, and they react slowly over the course of 5 days and then generate a black film at this interface. So we can take that film and we can, if we add a deposit, if we immerse a substrate in the solution, then the film just stays on the electrode and we can immobilize it like that, or we can collect the powder and then work with the powder as well. For the triphenylene hexathiolate, we see here, this is the synchrotron powder XRD data. We see peaks at low angles, suggesting that we have long range order in the AD plane. And this peak here corresponds to a distance of 2 nanometers, which is our pore diameter. Another peak that I want to emphasize is this broad peak over there that corresponds to the distance of about 3.3 angstrom. And that would be the pi-pi stacking interaction, but we don't have enough information to know how the layers stack, if they are in eclipse conformation or slip parallel, which is very common for two-dimensional materials. We are planning to do additional studies in the future to get information about that. But what we showed very early on is that as we decrease the pH of the solutions, we see increases in current. And then at pH 1.3, we saw very high current densities, and we were able to show that indeed these materials can generate hydrogen with 100% Faraday efficiency. So again, that was exciting. But we had two questions regarding these two materials. So first of all, this overpotential 530 millivolts for the triphenylene hexathiolate is quite large. Can we optimize that? Then the second question is, why are these two materials based on those two different ligands so different? Because if you look at the active side, they should be relatively similar. What is going on? So to get more information about that, then we decided to optimize each material independently. And we started with the benzene hexathiolate. In this case, we can deposit the material directly on the electrode. And that's how we did the electrochemical investigation. And then we briefly checked here different metal centers, cobalt, nickel, and iron. Cobalt was by far the most efficient one for hydrogen evolution. We can also use electrochemical impedance spectroscopy, and that gives us information about the charge transfer resistance and how well the material is integrated with the electrode. Here we decrease the thickness of the material from 23 nanometers to 250. And when we do that, we see a decrease in the overpotential, so better performance. Up to a point, if we go to 1 micron, we see an increase in the overpotential. So the reason this is the same data, but now plotted again as the function of the 250 nanometer film here. So what we see, then we measure the double layer capacitance. And what we observe is that the film, the 250 nanometer film was the one that had the highest double layer capacitance, and that is proportional with the electrochemical accessible surface area. So the 1 micron film, you physically have more cobalt there, but it's actually not electrochemically accessible. So that was our explanation of why that material had the best performance. And then we also looked here at imaging as well. And again, the 1 micron film had just overall a lot of cracking and poor integration with the electrode. The thinner films have nicer morphology and smoother morphology. So then we tried to, and then once again here to, we were able, again, by using this technique and increasing the thickness, we were able to decrease the overpotential by about 150 millivolts. So now we try to use the same technique for the triphenylene hexathiolate ligand, but this did not work. And it was primarily because, so we synthesized the materials from the same batch of the electrode, but we deposited on here 3 different electrodes, and you can see that there's drastically different behavior. So what we noticed is that the material would actually sometimes just peel off from the electrode and float in the solution. So we decided that we need a better deposition method. So in this case, again, we weren't able to deposit the film directly on the electrode because the way we synthesize the layers are invert and it doesn't work for this material anymore. So then we decided to use Nafion, which is a proton permeable membrane, and that is quite commonly used for 2D MOFs in particular. And that kept the material on the electrode, was more reproducible, but the material had quite high charge transfer resistance. So then we decided to add carbon black, which is a common conductive additive. And when we do that, we see a drastic increase in performance. The overpotential is now decreased by a substantial amount. And of course, we've done the control experiments with Nafion and carbon black. There's no activity. And then we can optimize the amount of carbon black. I think, sorry, 24% here was the best performance. And then we can also optimize the amount of loading that we're adding as well. Again, this is similar with the previous studies that I showed you, where we can increase the thickness. Here, we're tuning and increasing the loading. And again, it works. The performance increases as we increase the amount that we're depositing up to 20 microliters. And then after that, there is a decrease in performance. So 20 microliters is the best performance. And then I highlighted here our results compared with the cobalt THD by itself. You can see that we were able to decrease the overpotential by 400 millivolts, which is a lot. And then the taffel slope decreased as well. So basically what that tells us is that when we adding the carbon black, we're also changing the rate determining step as well in the reaction. Before carbon black, one more step was rate determining because its value is higher than 120 millivolts. But after adding the carbon black, we have a combination of taffel and Herovsky. That's the rate determining step. So again, to summarize this part of the talk, we were able to decrease for the first material to optimize the performance by increasing the thickness. For the second material is by making that incomposite. So coming back to the question, why were they so different? So now if you look at their electrochemical activity, it's relatively similar, right? So coming back to the question, why were they so different to start with? It turns out that their room temperature conductivity is different by 3 or 4 orders of magnitude. So the material that showed was initially more conductive, this benzene hexathiolate, showed higher activity as well. But if you add carbon black to suppress some of these bulk properties, then you get comparable values with the other material as well. So basically what that tells us is that conductivity is actually really important. And in the end, we want to develop a material that is both conductive and electrochemically active as well. And then here we have a comparison between our material and platinum on carbon under the same conditions, pH 1.3. And you can see that our material is just 100 millivolts higher over potential relative to platinum on carbon, which is quite exciting because we have only inexpensive elements. So again, to get more information about conductivity and how important it is, the role of the metal center, we became interested in looking at other metal centers as well as combination of other metal centers, mixed metals. So we looked at iron, but that is not a very good hydrogen evolving catalyst for this triphenylene hexathiolate ligand. We see the taffel slope is very high. Faraday efficiency is in the 70%, and then high charge transfer resistance as well. However, the two materials have very similar powder XRD pattern, cobalt THD and iron THD. So then we said, well, maybe let's give it a try. Let's see how mixing them together, what type of materials we would get. So using, again, that interfacial method, if we have a one-to-one initial ratio of the iron and cobalt precursors in our initial mixture, we only get actually a 5% incorporation of iron, and the rest is cobalt. So iron incorporates much slowly in the material when it grows. So then we change the ratio, and then to get about 50% of iron and cobalt, we had to use 100-to-1 ratio between iron and cobalt, and then we went 1,000-to-1 to get 70% iron, and then the rest is cobalt. So then we looked at the powder XRD pattern. Again, they're similar here. This is the cobalt THD by itself. Again, they're very similar, all of them. So then we looked at the electrochemical properties, and what we see is that, again, cobalt THD is very active. And then, but as we start introducing more iron in the framework, we see that the charge transfer increases quite a bit here. So these materials have as they have more iron incorporation to charge faster increases substantially, and then the Tafel slope also increases substantially as well. And then, well, when we look here, so both as we have more iron incorporated, the Faraday efficiency decreases, and then the turnover number per cobalt decreases as well. So what that tells us is that actually that iron is not an innocent spectator there. It's actually kind of detrimenting catalysis in this case, because the turnover for the cobalt should stay the same if iron has no effect. So our conclusion, we look at the XPS before and after, we see changes in the iron XPS spectrum, suggesting that the iron probably gets reduced. And our explanation is that it can basically a trapped site, maybe by getting reduced and decreasing the conductivity of the entire material as well. And it's that's the reason why it affects is performance. So then we decided, okay, well, maybe iron, it's not a good combination. Let's look at different metal center. Let's look at nickel and then mixed metals of nickel and cobalt. So nickel by itself, and here I want to mention actually the molecular catalyst first. So the nickel molecular catalyst was shown to just decompose in aqueous media. It makes a nickel sulfide film, containing film. However, when it is incorporated in a MOF, it is stable. So these were studies by Feng that were reported in 2015 with this nickel triphenylene hexathiolate framework that was synthesized using the Langmuir-Blodgett technique. And they show that the monolayer is quite active and has relatively low overpotential. So then, however, they didn't report any Faraday efficiency or any control potential electrolysis. So we decided to study further using the method that we developed, that the in-composite method. So we synthesize here the material in 3 different methods. The first method is when we add NMP, so N-methylpyrrolidione is the base that solubilizes some of this triphenylene hexathiolate. I forgot to mention that in the cobalt PHT synthesis as well, but that helps in solubilizing that ligand. And then when we sonicate it, we get that suspension that I showed you in the previous slides. So this is what we used in the first conditions, and we didn't add any charge compensating cations. In the second synthetic methods, we add charge compensating cations, such as sodium bromide. And then in the last one was just solvothermal synthesis when we had PHT and NMP and nickel acetate all in one solvent at 70 degrees Celsius. So then we look at the performance of all of these 3 materials. The first one had very high overpotentials and high Tafel slope, so it was not very efficient. And then also the current decreased very rapidly, and the amount charge passed was very low. For the second material, when we add sodium bromide, the film is a little bit more stable now. So we in the first case, our explanation was that because of the repulsions, the material just comes off from the electrode. When we add sodium bromide as a charge compensating cation, the film is more stable, stays on the electrode. And then we can change the thickness here from 2200 to about 1700 nanometers. And then we can also see here some small changes in the XPS signal when we add sodium, suggesting that sodium has a weak effect there. And then the overpotential is a little bit better, not as great. The last material that we looked at, it was this solvothermal condition, had a very high, great performance, much lower overpotentials and much better Tafel slope. And then it was very stable here for several hours, and then had a high Faraday efficiency of about close to 100%. So then we decided, okay, well, if nickel actually and that optimized material works well, then let's try mixed metals of nickel and iron to see, nickel and cobalt, to see if we can maintain both the high activity and selectivity as well. So in the literature, it was reported that, in particular for this COPS 367, that they can actually dilute the number of cobalts by introducing copper. that is not electrochemically active. And then when they do that, they increase the turnover number frequency per cobalt, and that increases. However, at the expense of the Faraday efficiency. Faraday efficiency decreases when you have that substitution. So we were once again interested in seeing if we can maintain both the Faraday efficiency and increase the turnover number. And the answer is yes. So we made here, we generated this mixed metal materials where we have 100% cobalt or 22%. This is the powder SRD. These are the feeding ratio, which are now closer. This is done through the solvothermal method. So now the feeding and the obtained ratios are actually much closer together. They're not as different as what I showed you before using the interfacial method. Okay. Here again, we obtain 4 different materials varying the cobalt concentration from 100% to 5% cobalt in the material. So as we decrease the cobalt content, we see, first of all, cobalt THD is very active, but then the other materials are actually quite similar. And then when we plot the normalized current dividing by the amount of cobalt, we see that these materials that have some cobalt incorporated in it, they are actually quite active. So then if we plot the turnover number for cobalt, we see that in particularly for this material number 4, where we had 5% cobalt, we actually have quite high turnover number. And I forgot to mention that all the Faraday efficiency for all these materials is actually unity. So we can maintain the high Faraday efficiency and then also increase the turnover number for cobalt as well, which is very exciting. So with that, so there is a 200-fold increasement there relative to the cobalt THD by itself. So with that, I'd like to stop here. Again, thank you, the organizers, for including me in the program. I'd like to thank my students for their hard work and dedications. Thank you for your attention, and I'll be happy to answer any questions.
Like a much slower rate. So I wonder if that affects the distribution within the layer. So one could assume that because the kinetics favors the cobalt incorporation, there's more cobalt in the middle of the sheet and more iron towards the edges. Is this something that you've looked into?
That's a very good question. I think we did EDS mapping for all of them, and we don't see a very large difference between the different ratios. So we assume that is homogeneously distributed throughout the material. Yes.
So can you comment on the particle sizes?
I think they're on the order of, well, we make the materials, the films are quite large, but then when they break up, when we do the workup, when we wash them with water, with methanol. So, and then when we make the ink, we take that mixture and then sonicate it as well. So they become, I don't remember the exact size. But
thank you very much.
Great talks, Miranda. Do you know if the crystallinity of these materials is maintained after the electrocatalytic function, especially in such high acidity?
Yeah, that's a very good question. So we definitely have looked at the XPS before and after, and it's similar. Crystallinity, I think we have tried to do that, and I think the powder SRD looks similar, but we obviously have to collect a lot more material, right? And I think we were able to do that, and we see similar crystallinity by powder SRD. So yes. But that is a very good question about the acidity. So pH 1.3 works, but we haven't gone much further than that because there is possible, especially I think with nickel, might be leaching more of the nickel in the electrolytes. Actually, even under certain conditions, nickel THD does leach a little bit more. But we actually, in that case, for nickel, we see that there is excess nickel that is trapped in the material. Because the ratio is actually higher than what we would expect the nickel sulfur ratio. Yes. So the nickel that might be leaching could be the ones that is the charge compensating cation, because each side for nickel would have a 2- charge. For cobalt, it's a -1 charge. Yes. Pues Professor Julia Aguilar.
Thank you. First, my apologies because I'm speaking Spanish. Sorry. Well. Bueno, primeramente voy a hablar un poco sobre la investigación con mujeres en México. Esto lo saqué o lo puse aquí de una investigación que se hace de una asociación que hay aquí en el país que se llama Sistema Nacional de Investigadores y nos arroja que en el 2024, en el 2024 se ha reportado un incremento de 17,000 mujeres que se están dedicando a la investigación. Este incremento nos quiere decir que tenemos un 66.9% comparado con el 2018. Y también aquí se habla sobre todo de mujeres que están haciendo o que tienen becas postdoctorales. Se ha incrementado también un 6.7% desde el 2018 al 2024. Por lo tanto, entonces, las mujeres nos representan un 57.2% del total, dentro de 267,114 que están haciendo posgrados. Y del 2023 al 2024 también están dentro de la academia. Entonces, como podemos ver aquí, pues año con año el incremento de la investigación de mujeres o con mujeres, pues va hacia adelante. Entonces, ya hablando un poco del tema que hago yo, lo que vengo a contar aquí es sobre todo cómo inicié en esto de los MOFs. Yo estudié zeolitas en el ITQ en Valencia y bueno, pues las zeolitas sobre todo las utilizamos para hacer catálisis, ¿no? Y aquí sobre todo la catálisis heterogénea, que sigue los pasos que estoy poniendo aquí. Estos que son fenómenos de transporte, fenómenos difusionales, que todos aquí ya sabemos, y sobre todo la catálisis heterogénea, ¿no? Entonces, aquí pongo las 3 formas más importantes de catálisis que se dan, que es la homogénea, la heterogénea y la enzimática. Y hablando y abocándonos un poco a la química verde o el cuidado del medio ambiente, bueno, pues vemos aquí que el uso de catalizadores y biocatalizadores mejora nuestra eficiencia y es muy importante para usarlos hoy en día. Entonces, resulta que México, siendo un país que come mucho maíz y que somos muy maiceros, pues entonces ustedes seguramente ya han de haber probado las tortillas, los tacos, etcétera, ¿no? Bueno, ¿cómo se llega a tener estas tortillas y todo el maíz? ¿Cómo no lo comemos? Bueno, pues están las mazorcas. Estas reciben o hacen un tratamiento con calcio en una gran tina como esta que estamos viendo aquí y nos va a salir un caldo residual al cual llamamos nejayote, ¿vale? Dentro del nejayote, bueno, a todo este proceso se le llama nixtamalización del maíz. Entonces, este nejayote es un líquido muy contaminante. De hecho, en los molinos y las tortillerías lo arrojan a la coladera, ¿vale? Pero aquí tenemos polisacáridos, fibras, sólidos, proteínas y un alto demanda de oxígeno, ¿no? Por los sólidos suspendidos, y por lo tanto, pues no es bueno que se eche al caño. Entonces, pues aquí empezó mi colaboración con el doctor Ibarra y con el doctor Manuel Sánchez de España, y empezamos a trabajar, ¿por qué no?, hacer catálisis heterogénea con MOF para poder utilizar algunos compuestos importantes de este caldo que es contaminante. Bueno, dentro de este caldo o de este líquido existen muchas moléculas importantes. Una de ellas es el ácido ferúlico. Se puede obtener el ácido ferúlico de este caldo y por lo tanto se puede también obtener, o hemos obtenido, lo que es la vainillina. México es un productor muy bueno, ahora ya se está acabando, de vainilla, que proviene del estado de Veracruz y que sale de estas vainas que tenemos aquí. Sin embargo, bueno, sabemos que también la vainillina, que es uno de los principales componentes que está en la vainilla, aparte tiene el ácido vainillínico y otros compuestos fenólicos también, pero bueno, recientemente sabemos que el 1% de la producción de la vainilla se extrae de las vainas que tenemos aquí. Y cuando se hace por vías sintéticas, pues se hace a partir de bencenos, de eugenol, de ácido ferúlico, de curcumina, etcétera. Pero se tienen muchas horas para poder obtener la cantidad X o que se quiera obtener de vainillina. Entonces, pensamos, ¿por qué no hacer, como he dicho, catálisis heterogénea con el ácido ferúlico? Bueno, aquí les muestro varias formas de obtener la vainillina. Ya sabemos, con las vainas que se tienen aquí, con arroz, con el propio maíz, con la glucosa que se tiene del maíz, con clavo, con la curcumina, etcétera, para poder llegar a ella por diferentes formas, ¿no? Bueno, entonces, ya volteando un poco hacia los MOF, sabemos que son muy importantes para la catálisis porque pueden actuar como catalizadores ácido-base o como catalizadores redox. Entonces van a tener ellos, algunos, la presencia de open metal sites, que son importantes para llevar a cabo la catálisis, tienen altas superficies porosas y tienen altas áreas superficiales. Por lo tanto, pues son las características que los que hacemos catálisis heterogénea buscamos. Entonces, aquí, bueno, pueden ver que se obtienen compuestos de química fina, ¿no? Por la oxidación de algunos compuestos, obteniendo benzaldehído, óxido de estireno y en este caso, bueno, la vainillina. Entonces, lo que hemos hecho es utilizar el MOF HCUST1 para la oxidación del ácido transferúlico que obtenemos del caldo, lo extraemos de ahí. Claro, también hicimos con ácido ferúlico o ácido transferúlico comprado, pero bueno, también lo obtenemos de ahí, hacemos la reacción como ahora les voy a indicar y aprovechamos de ahí los metales o el metal de cobre 2 que se tiene en el HCUST. Entonces, ¿por qué el ácido ferúlico es importante? Bueno, pues porque va a actuar como un componente importante de muchas cosas, ¿no? Pionero en la producción de vainilla, como para poder hacer colágeno, para poder estabilizar la vitamina C, etcétera, etcétera. Entonces, también es un compuesto importante. Entonces, ya que, ¿cómo nosotros vamos a saber si de verdad obtuvimos el ácido ferúlico? Bueno, hicimos una resonancia y, bueno, pues aquí está el ácido ferúlico que obtuvimos del nejayote. Entonces, ¿cómo hicimos la reacción? Pues la reacción la hicimos poniendo el ácido como oxidante el peróxido H2O2, como un promotor acetonitrilo y en etanol, en reflujo, etcétera. Aquí está, ¿no? Con detenimiento, la temperatura de reacción fue 100 grados centígrados en vacío y la reacción se llevó suspendiendo el MOF en el matraz, etcétera, en reflujo durante 3 horas. Se filtró, se lavó, se evaporó, se concentró y, bueno, pues se hizo la separación por cromatografía de columna. Entonces obtuvimos aquí lo que es la vainillina con un poquito, muy poquito de ácido acético, ¿no? Esto cabe mencionar, fue la tesis de maestría de una chica que estuvo haciendo todo esto. Bueno, entonces, de verdad vamos a ver si el HQ se mantuvo en su estructura o no. Bueno, pues esto aquí está mostrándonos que es antes de la reacción y después de la reacción. Y pues se mantuvo muy bien la estructura del HQ. Pero entonces, ¿cómo podemos saber si de verdad con la activación que se le hizo antes de la reacción al HQ, teníamos libres los centros de cobre más 2? Pues entonces se hizo esta corrida de espectroscopía de infrarroja para ver aquí si de verdad cuando hacíamos el tratamiento a vacío, se iba el agua que estaba absorbida o ahí agregada en el metal de cobre 2. Y como lo podemos ver, bueno, pues sí, ¿no? Aquí está el HQ como recién recibido o como se tiene. Después es activado en aire y activado en vacío. Entonces pueden ver aquí que en vacío pues ya no tenemos agua ahí absorbida. Aquí, bueno, solamente se muestra lo que sería el TGA para ver pues cuál es el decaimiento estructural de este material, que es pues bastante mayor pues la temperatura que puede soportar. Entonces, después de que se hizo la reacción, ¿cómo podemos comprobar si de verdad obtuvimos la vanillina? Entonces, también hacemos RMN de carbono 13 y de protón. Y pues sí, obtuvimos realmente la vanillina. Entonces, ¿cuáles son las mejores condiciones que tenemos para poder obtener este producto? Bueno, aquí se tienen diferentes cantidades de catalizador y tenemos aquí muy buenas conversiones, bueno, rendimientos, perdón, de la vainillina. Como pueden ver, tenemos un 98%, cuando tenemos 3.2 y 4.8 tenemos un 98% también. Bueno, esto se repitió por varios ciclos y el catalizador se mantuvo siempre sin perder su cristalinidad o su estructura. ¿Sí? Y también se mantuvo un rendimiento bastante alto de la vainillina. que no pasa esto. Ya no pasa. Ok, gracias. Antes. Una después. No, después, a ver. Ahí, gracias. Bueno, entonces, también hicimos esta reacción con el MOF 74 de cobre. Obedeciendo también a todo lo que es amigable con el medio ambiente, pues entonces nosotros sintetizamos el MOF 74 en metanol y a temperatura ambiente. También se activó en vacío, etcétera, y se hizo también la espectroscopía para ver si teníamos los sitios libres, en este caso también, y bueno, la transformación que sufrió aquí el ácido ferúlico fue pues bastante buena, de 71 y 97% también de selectividad. Entonces, en esta gráfica nosotros podemos ver que también utilizamos nitrato de cobre, un blanco, o sea, sin catalizador, para ver si realmente el MOF era el que estaba haciendo la conversión. Y como pueden ver, pues sí, el MOF 74 es el que funcionó bastante bien para esta reacción. Por lo tanto, bueno, pues es importante tener en cuenta esto. La siguiente. Bueno, entonces, también se planteó en conjunto con los teóricos, pues un patrón de reacción, ¿no? Donde vamos aquí teniendo, pues, el ácido ferúlico, se forman los cationes, desprende o está aquí, pues ya absorbiéndose de alguna manera en los centros activos, hasta que llegamos a obtener pues la vainillina. Entonces, seguimos trabajando con diferentes materiales. Hemos trabajado también con la oxidación de estireno, con el MOF 74, con diferentes metales, cobre, zinc, cobalto, etcétera, con bastante buenos selectividades. Una cosa importante que hay que señalar es que estos materiales son muy selectivos, ¿sí? Hacia la catálisis que uno quiera pues realizar. Estamos empezando con hacer adición de CO2 a epóxidos, mezclas también de MOF bimetálicos para aplicarlos también a todas estas reacciones. Se hace también pruebas de absorción de CO2, H2S, SO2 y últimamente nos hemos metido en la inmovilización de enzimas en MOF con el 1053. Entonces, bueno, pues esto es un tema súper bonito que entra también dentro de lo que sería el cuidado del medio ambiente, porque lo que estamos haciendo es, queremos convertir lo que serían los fármacos emergentes que están hoy muy de moda en algo que no sea poluyente, ¿no? Y bueno, ya para concluir, pues aquí muestro algunas colegas que actualmente pues estamos trabajando en conjunto, que sería la doctora Aida Gutiérrez Alejandre de la Facultad de Química, la doctora Dora Solís Casados del SIX de la UAM UNAM. Ellas dos apoyan bastante en la parte de caracterización, ella en cosas de espectroscopía infrarroja y absorción in situ, la doctora Solís en el XPS y bueno, la doctora Asunción, que es la experta, por decir, de la inmovilización de enzimas en los MOFs. Y bueno, muchas gracias. También cabe resaltar que en el octubre de septiembre, se hizo un curso de MOF en mi universidad y obtuvimos estos HQs súper bonitos. Bueno, muchas gracias.
Y las diferencias que habría entre la catálisis utilizando el ácido ferúlico comercial puro y cuando utilicéis el caldo, que habrá pues muchos otros productos y debe de afectar quizás negativamente, si habéis evaluado la diferencia y cuánto tiempo tarda quizás en desactivarse, si lo habéis podido reciclar o...
El ácido ferúlico.
No, la catálisis. ¿Cuántas veces?
No, la catálisis se mantenía, llegó hasta un plato y el ácido ferúlico lo, ¿cómo digo? Le quitamos todas las impurezas al que obtuvimos del caldo.
¿No funcionaría si le ponéis el caldo directamente al ser tan selectivo?
Pues es que quién sabe qué obtenemos, porque entonces ahí tenemos ferúlico, tenemos curcumina, un montón de compuestos fenólicos, que estaría bien echarlo al caldo y pues a ver qué nos sale, ¿no? Pero pues un montón de cosas.
Vale, gracias, muchas
Sí.
gracias.
Hello, nice to meet you. I'm Jin Young Kim, assistant professor in School of Chemistry Education at Seoul National University. Before start my presentation, I'm very honored to be here today, and I'm very thanks to organizing committee who organizing this beautiful conference. So today I'm gonna talk about my recent research topic, that is the identification of corrosive vapors using MOFs-based sensor. Okay, so I'm sure that most of you already know the exit. So exit is the essential chemical in modern chemical process to produce these various type of chemical product. And however, due to their high reactivity, if you use these actually chemicals with careless, then you might see this terrible accident in your place. So to prevent this accident, identifying, the detection and identification of this actually chemical is very important, because depending on the actual chemicals, the first aid protocol or the evacuation protocol might be different. So you might think that we already have very good actually sensor which can detect actually vapors. So which actually sensor already have very good sensitivity, and some of them are already commercially available ones. But the problem is the identification of these actually vapors. How we can identify this actual vapor? Actually, this sensor, they only detect the actual sensor, actual gas, but they cannot identify which actual gas are exposed. So our project was started at this point. Then how we can identify this colorless actual gas? Actually, I'm sure that most of you already know the answer, because that is very simple theory that is just utilizing ligand field theory. I think you already know that in metal complex, depending on the coordinating ligand, the metal complex color will be changed. And actually in the anion part of this actually vapors are very good ligand for this metal complex. So our answer was very simple, just utilizing metal complex. So we designed the MOF decoder as like here. First, we choose MOF AOA, that is very actually stable MOF. Then, positively, we decorate copper EDTA on this MOF cluster, MOF zirconium cluster, which can directly expose to the environment. And actually, this copper EDTA is meta complex, and this is colorimetric center for identification of this active gas. So if active gas are exposed, then our decoder shows the characteristic color change. So finally, we can identify which active gas are exposed. So here is the real static conditions. So first we prepared MOF AOA, then post-statically we introduced copper EDTA onto zirconium cluster. After post-modification, the MOF AOA crystal structures still retain compound by PXRD pattern, and also the copper EDTA was decorating on the zirconium cluster compound by this XPS spectra. And finally, this copper EDTA that is colorimetric center shows 6 coordinated geometry compound by the UV-Vis NIR spectra, and they show characteristic 6 coordinated copper DD transition. So with this result, we conclude that our colorimetric decoder looks like this conformation. And then we just trying to expose acid gas, real acid gas. First, we try to expose this concentrated hydrogen. Oh, sorry. And at first time, we thought that this color change might come from the MOF structure decomposition, but it was not, because when we measured the PXRD pattern, as you can see here, the crystal lineage is still retained even after hydrogen chloride exposed. Then we conducted several experiments to understand that this the origin of this yellow color change. First, we conduct SGM EDS mapping, and we found that after hydrogen chloride exposure, the chloroligand are participate in our sensor domain. And then we found that this chloroligand are make bond with copper ion compound by Raman spectra. And finally, this copper and chloro complex shows 4 coordinated complex compound by UV-Vis NIR spectra. And actually this one is yellow one. So with this result, we conclude that the yellow color change is originating from the geometric environmental change of this copper complex. And then we just think about the, actually we exposed to the highly concentrated hydrogen chloro gas is almost 15,000 ppm. So we just wonder how, what happened if we decrease the concentration of this hydrogen chloro gas. So we're trying to decrease more than 100 times. So we exposed to 120 ppm. And as you can see, of course, the detection time is a little bit longer, but still the characteristic color change, cyan to yellow, is clearly shown in our MOF. And also comparing with the non-porous metal complex like copper EDTA or copper acetate, our MOF sensor shows quite fast color change compared to this non-porous one. So we conclude that the copper EDTA in our MOF sensor can directly expose to the environment. So because of that, they can effectively show color change with exit gas evaporation, exit gas exposure. And then we just think about the cyclability. So surprisingly, when we add this yellow colored one into water, then just directly the color change was color changes to original cyan colored one. So it means that it regenerated. And when we compound by ISP, we conclude that 80% of copper is recovered, successfully recovered. So they are now prepared to next round for exposure. And actually this regeneration can, this MOF shows 3 times of regeneration. And also this regeneration is confirmed by UV-Vis NIR spectra and PXRD data. And after this result, we were very happy, but we have big question. That is the decoding mechanism. Actually, the chloro ligand is the really weak ligand. And we just wonder that how this weak ligand can steer copper ion from strong chelating EDTA ligand. So we conduct several experiments to understand this decoding mechanism. So first, we prepared 3 types of different aqueous solution, which containing same 4 mole of chloro ligand. So the first one is acidic solution, and the other 2 is almost the neutral one. And surprisingly, only in acidic condition, our decoder shows the yellow color change, which means that not only chloro ligand, but also proton is participate this color change mechanism. And we found that the role of proton by after measuring FTIR and XPS spectra. So after hydrogen chloride exposure, the protonated carboxylate peak, that carboxylic acid peak, is increased, and also the protonated nitrogen peak, protonated amine peak is increased after hydrogen actually gets exposed, which means that this proton now protonated EDTA. So because of then the protonated EDTA now cannot chelate in copper ion anymore, so the copper ion will be released to the environment. Then because of that, the chloro ligand can react with this pre-copper ion. So which means that not only chloro ligand, but also proton is essential for the colorimetric decoding of acid vapor in our system. Okay, after understanding this decoding mechanism, we concluded that not only hydrogen chloride, but also other acid gas, they will show some characteristic color change with our MOF system. So we exposed to not only hydrogen fluoride, but also hydrogen bromide and iodide, and we shows this beautiful color change. And also this EDTA is very strong chelating ligand, so they can chelate not only copper ion, but also other metal ions. So if we expose to the iron instead of copper, then you can synthesize this metal, another metal decoder system. And also they shows this characteristic color change. And how about the mixed metal ion system? This EDTA can chelate not only copper, but also cobalt. So even in single decoding domain, copper and cobalt are homogeneously distributed. And also because of that, now we can extend decoding actually gas up to 6. And with this result, we want to go after this, see this result, we just wanted to make real gas decoder. So now we was this color change can be detected by not only by our naked eye, but also now it can record by camera sensor. Actually, this is a very good point because now we can do 24-hour on-site monitoring. And also now we can extract the RGB value depending on the exposure time, which means that now we can quantize the color change of this sensor. So with this result, we just wondered then how about the other acid gas? So we exposed to other acid gas like the hydrogen fluoride and bromide and iodide. Of course, the color was changed, but here is the big problem. That was it takes too long time. So it takes more than 20 minutes, which means that we might be die before we identify this actual gas. So we try to decrease identification time, but how about 2 minutes? I'm sure that none of you cannot decoding which actual gas are exposed to our actual decoder. Actually, human can't, but camera sensor, they can. As you can see here, even after 2 minutes, 2-minute exposure, they show characteristic RGB value change depending on the actual gas. So because of that, they can identify which actual gas are exposed to our decoder. So with this result, we conduct several analyses. And as you can see here, if we expose same actual gas, then they are well clustered together. And if we expose different actual gas, then they are separate from each other, which means that the computer now can identify which actual gas are exposed. So this was the first example of identification of actual vapor. So this result was published in Nature Communication this year. And after that, we just want to move to the next project. So due to time limitation, I cannot explain full story, but our goal was, how about base gas? I mean that we have so there's two types of corrosive gas. The one is actual gas and the other one is base gas. So we just want to decoding not only actual gas, also base gas. But actually this is very, very difficult because actual gas, usually they are electron acceptor, and also base gas, usually they are electron donor. So they have different characters. So because of that, they usually show different chemical reaction pathway. So it was really difficult to introducing two different identification mechanisms into one decoding sensor. But we did it. It was very simple, just using same strategy. But in this case, we didn't use EDTA, just directly introduce copper ion into zirconia cluster of MOF-808. Actually, this is already well-published method. We just utilizing this one. And if you use this one, then now we prepare the corrosive gas decoder. And as you can see here, if you expose to amine gas, then the cyan color changes to the more deep blue one. And as you can see, the pixel pattern is still retained, which means that this color change not from the MOF structure decomposition or change. But as you can see, the FTIR spectra, they shows coordinating, stretching, which means that the color change is originated from the coordinating of amine onto copper side. And if you exposed to actual gas or other base gas, as you can see here, they shows very characteristic color change, which means that our system is very good decoder for not only for actual gas, but also base gas. Of course, if we decrease concentration of this actual gas, then the detection time might be longer, but still compared to non-porous one, our decoder system is much better than the non-porous one. So the directly expose this copper ion into environment is very important. And of course, we conduct we make near MOF portable sensor. And if we conduct the HCA hierarchical cluster analysis, and we conclude that this sensor is real decoding sensor for this not only actual gas, but also base gas. Actually, was very surprised. Only after 15 seconds exposure, we can identify which exit or base gas are exposed. So this result was published very recently in Crystal Engineering Communication as invited paper. So because of time limitation, I couldn't explain everything, but if you are interested, please visit this paper and you can see the results. So all of this research was mostly conducted by Haejin Yu. She is here, and here is a group photo of my group. And as you can see, most of my group are composed of the female students. So I'm very proud of her. I'm very proud of my members, and thank you for kind attention.
Thank you for the beautiful talk. Have you looked at any gas mixtures, like dosing multiple gases at the same time?
Yeah, it's very good question. But if you see the mechanism that actually the copper will coordinating the ligand of this gas, right? But actually this copper ligand always have some preference of the coordinating ligand. So even though you expose mixture, they always, the copper ion always want to coordinating the more preferred strong ligands. So we cannot, our MOF system cannot act in mixture system.
Okay, thank you.
Kinetics. Yeah, actually, when we expose to the concentrated acid gas, we found that the different kinetics, but mostly that is because of the concentration of acid vapor. Oh, but in mixture case, the copper ion usually coordinating more preferred gas. So we cannot see, for example, A and B, even though the kinetic is different, but usually copper ion only binding to more preferred ones. So we cannot differentiate yet.
Correlations between acid strength and reversibility of the color for these materials? Like, do some reverse better than others depending on what acid you use when you soak them in water to reverse? Thank you. To reverse the color effect.
Oh, you mean the first project?
Right. So the 4 different acids.
Oh, yes.
Is there a correlation between acid strength and color reversibility?
Actually, when we conduct, so we tried several experiments with hydrogen chloride and hydrogen bromide and iodide. They shows good reversibility, but in case of hydrogen fluoride, when we add water, then some kinds of MOF still return to cyan color. But the problem is that hydrogen fluoride now dissolved MOF, AOA. So that was the problem.
So I'm going to introduce our next speaker before the break.
Yeah, thank you very much, Kanchi, for the kind introduction and also for placing me straight away between everyone and the coffee break. No pressure, yeah. Right. So then without further ado, I would like to just quickly get into it. Of course, if you have any further questions after the talk, you're always welcome to email me. I would like to start by firstly congratulating the organizers to this wonderful event. I've been enjoying it a lot and I'm looking forward to the next days as well. And I would also like to firstly acknowledge the contribution to especially all the students. So those ones are the ones in color. So in red, you have the students who have PhD candidates who have contributed to the synthesis. Bea did X-ray absorption spectroscopy, and Muhammad did most of the testing. One did the DFT calculations, and in black you have the supervisors. And where the inspiration comes from. And so I would like to start with the methane to methanol reaction, which is considered like a dream reaction in heterogeneous catalysis. And that is, of course, because methane is a quite abundant gas that is also a kind of a side product of many processes and also activities such as farming in the world. So it's also, of course, a fuel, but it's a very potent greenhouse gas as well. And it's kind of difficult to deal with on account of its apolarity and symmetry. So in any case, it would be very nice to be able to somehow contain it, to do something with it in order to make it easier to handle. And that's why its conversion into methanol is very appealing. That the challenge lies in the fact that so methane is a quite stable molecule. In order to activate it, to partially oxidize it, of course, we need to input quite a bit of energy. But once we've done this activation for one CH bonds, all the other CH bonds will be much easier activated. And therefore, typically what you do is to get this over-oxidation into carbon monoxide and carbon dioxide, especially, which we would like to avoid because these are not so valuable molecules. But enzymes do this kind of gentle yet powerful activation all the time, also under very mild conditions. And Julia already made the link between metal organic frameworks and enzymes and how to combine them. So I would just like to continue in that vein a little bit. And so this is the subject of this ERC Synergy Grant that I'm a local PI on. So here is the PI team. It's led by my colleague and neighbor and friend, Professor Uni Obia from the University of Oslo. And we also have, I saw in Serena's name in another presentation, I think in yours, yeah. So from Max Planck Institute, we have Vincent from the Norwegian University of Life Sciences, and Celia does a lot of the surface science and spectroscopy. So here the aim is to get inspiration from enzymes, notably from the lytic polysaccharide monooxygenase or LPMO enzyme, which is a copper-based enzyme, and it does ambient CH activation. It does it mostly for saccharides, but the idea is that perhaps we could learn from it and translate that learning into metal organic frameworks and to be able to design a catalyst that can convert methane into methanol under ambient conditions. And another inspiration comes from the particulate methane monooxygenase. So this is a methane monooxygenase enzyme, as the name suggests. But here the problem is that it has, while LPMO only has one copper site, so it's very well understood where the catalytic reaction occurs. In the case of PMMO, it's still a matter of debate which of the copper site, if any particular one, is the one that is active. And of course, taking learnings from from enzymes and translating into MOFs or integrating into metal organic frameworks is not a new concept. There is various ways of doing it. Julia also showed the addition of enzymes to metal organic frameworks. What we do is a little bit different. So we want to replicate to some extent the active site in the enzyme and integrate that into the MOF. And of course, the frameworks we use Well, there's a UIOs ones. Of course, you have to push the brand a little bit, but it's not only for that. But because when methane is oxidized, there is a lot of water that is also formed, and we need to have metal organic frameworks that are stable under the evolution of a lot of water and at relatively high temperatures as well. So that's why we need. I will be mostly showing results of UIO 67, but we also use 66 sometimes. So a little bit about MOFs. I mean, of course, I don't want to tell you anything about MOFs, what they are, but I think that metal organic frameworks really give us a very particular opportunity to translate and integrate enzymatic functions into man-made synthetic material. And what do I mean by that? So when we look at the protein structure, and I'm not a biochemist, but we can all appreciate that these are very, very complex structures. Yeah, so of course already the structure is organized at various levels, and I think that we can take those levels and integrate them into the MOF design. What do I mean by that? So when we look at, for example, the primary structure of an enzyme, then of course this will be the sequence of amino acids. And then we can take that and we can use this to design the active center. For example, we can make a linker that has an active center, which is very similar to the one that one can find in the enzyme. And actually, I would like to say that this is the current state of the art active site design when it comes to the integration of or mimicking of enzymes into metal organic frameworks. So here we're engineering the coordination spec, controlling the oxidation state and the coordination number, especially through the ligands. So this, of course, is linked to the primary protein structure. And then we can look at the secondary protein structure, so how the the sequence is folded, and then the whole line is how it's then folded up into each other, creating, in fact, getting some functional groups, some amino acids in close proximity to the active center, which on the sort of thread of the protein structure would be quite remote from the active center itself. So we can use this. These are the so-called second sphere effects. When you get from a, from this amino acid, you get a functional group which gets in close proximity with this one here. So this is called residual effects by the enzymologists. And here we get non-coordinating molecules and functional groups that are still in quite close proximity of the active center. In addition, they can also act as proton and electron donors. So I have some, so Raphael is working on this, and there were some master student, Laura and Yun, that also work towards this. And this is looking at the sort of the translation of the tertiary structure of the enzymes into the MOFs. And then we get the long range effects. In the case of PMMO, for example, it is known that there are hydrophobic pockets not far away from the active center, whose role is to really increase the concentration of methane to provide a larger supply of methane to the active center. So these also, we can work with the spatial requirements around this. So this is the quaternary structure, and Ingeborg and Helena have been working on this. And so we work with the copper-based catalysts. It's just without going into a lot of detail, but it is also well known that there is a strong interplay between the oxidation state of copper and the local environment. So the copper-2 likes square pyramid, whereas copper-1 likes more sort of tetrahedral-like or trigonal pyramid, bipyramid structure. So with that much delay, I would like to really forge into the different levels of designing or sort of translating enzyme structures and integrating them into the metal organic frameworks. So just a visual reminder of the RPMO and the PMMO here. And these are some linkers that we have designed that replicates this kind of a first coordination sphere within these two enzymes. So these are always histidine based. So we're trying to put a lot of nitrogens around the copper. So here is a beautiful example. This was done by Barbara. So Sylvia asked me a few years ago that Barbara designed this molecule, can we put it into a MOF? So together with Barbara, we came up with the sequence to designing the linker based on this molecule, and then integrating the first one of the linkers inside of the frameworks, and then adding the copper and another linker, so kind of sandwiching the copper in between. And the beauty here is that this looks like a bipyridine, but because it's got methyl groups on it, it kind of stops the bipyridines to get into the squared arrangement. So it kind of forces the copper into the copper 1 state, which is also the catalytically active state. And here we were able to also demonstrate that this copper, so spectroscopically, so this copper 1 state is preserved when the structure is inside the MOF. And also we were able to test this activity. So here we were looking liquid phase testing. So we're not as good as nature, I must say, not yet anyway. So we look at the oxidation or the activation of CH bonds in cyclohexene, and we used tetrabutyl hydroperoxide as the oxidant. So yeah, it's a zoo, really what we get. And we were also able to model what kind of products we have and come up and rationalize the reaction mechanism. And also, sorry, my time is gone now, but we were also looking at, this is another example in which we try to integrate the copper in between the MOF node and the histidine, which is grafted onto a defective site. So here we grafted with the C terminus on the histidine molecule on a node, and then on the sort of vicinal node, we graft the copper ion to ideally get a structure like this. Now, maybe, well, and this is all nice and crystalline, as you can see, there is no change, but maybe I won't give away much when I say that when we work with, and we worked with copper 2 in this case, that the copper 2 actually will have preferred to go onto the node instead of necessarily linking between the histidine and the node itself. So this was based on a joint theoretical and X-ray absorption spectroscopy investigation. However, when the copper loading was high enough, then there were some cases in which the copper could bridge between the node and the histidine itself. And then we also looked at the same mechanism, so between the cyclohexene activation with this organic hydroperoxide. So this is based on previous theory survey. And so what the literature says that both the catalyst as well as this hydroperoxide oxidant is necessary in order for the reaction to occur. And then it can go either way. But the key here is that in both cases, you can see that there is a radical molecule that is produced. And then from that on, the reaction just is let loose. So it's a radical chain reaction that takes place afterwards. So the catalyst is only needed in the first step of the reaction in this case. And this was actually, it's a lot of data here, but this was also demonstrated experimentally that it is the case also. So this was what I wanted to show about the coordinations, the first shell effect. And I would just like to maybe focus a little bit more on the second sphere effect, which is a little bit maybe more novel in terms of the concept itself. So once again, we were looking at the enzymes themselves. And so this is the RPMO and this is the PMMO, if I'm not mistaken. But what you see here is the histidine base in both cases. And then there are these molecules, in which these are not coordinating to the copper. So this is a tyrosine here, and this is a glutamide amino acid, but they are in close proximity, and especially they ensure proton transfer in the case of the enzyme. So we are working with this linker here. We did some post-synthetic linker exchange to incorporate these linkers into the UIO67 and then added copper. And what we wanted is a very simple approach in the first instance. So we took these molecules, so phenol and propionamide, which are supposed to replicate these residues in the different enzymes, and we just infused it into the MOFs, hoping that they would end up somehow in close proximity, but not coordinated to the copper. As I said, this is a very basic first approach we took. This is porous and also crystalline MOF we got afterwards. But what we observed is that, firstly, the phenol didn't go in at all. And then the propionamide stayed inside the pores of the MOFs. In fact, it stayed so close to the copper that it actually coordinated to it. But the reason to that is that it underwent this kind of tautomerization during the infusion. And then, so in a combined XRFs and also infrared and NMR work, we were able to, and DFT as well, were able to show that it is indeed coordinating to the copper. So we alter in a very cheap way the coordination spare of the active center. But when we looked at the testing, what we found out is that this molecule gets removed very, very quickly in the liquid phase. So we still think that this is an interesting method, but somehow we will have to tether this molecule to maybe another linker in order to test this effect more efficiently. Here we observe the same reaction mechanism as we did in the case of the copper grafted on the nodes. And just finally, a few words on the sort of this third level of integration. So looking at long-range effects. And this is just an example. So we have more ongoing work, but I just want to exemplify this a little bit. So here what we did is we started from this linker, which is a bidentate linker, as opposed to the tridentate ones we used before. And on this R group, we added different groups of different barkiness. So we had hydrogen, phenyl group, and xylyl as well. So we integrated these post-synthetically into the MOF. And also I would like to say that not only there is a difference in the barkiness, but also in the hydrophobicity of these groups, of course. And then we looked at their water uptake ability to assess the hydrophobicity. And basically, there are two things that you should observe here. So on the one hand, you can see that the more hydrophobic the group, actually, the larger the ultimate water uptake or water vapor uptake in these MOFs. But the other thing that when you can look at is this ascending part of the isotherm. Then you can see that the earlier the onset, the stronger the interaction with water. So that is a little bit more in line with our chemical intuition that the more hydrophobic the group, the weaker the interaction with water. Yeah, so we haven't made new chemistry, so that was reassuring. The reason to the higher uptake in the xylyl actually is because the ones that are less hydrophobic decompose much quicker when exposed to water vapor, which is a bit sad even for a UIO MOF to decompose water vapor, but this just happens. But we can protect it by, for example, adding xylyl groups in them. And finally, so just to show that initially they were all crystalline and porous, and we were also able to graft copper on the bidentate linker. And the porosity is really, or the surface area is really in line with the increasing molar mass. So the sort of the molar surface area, if you wish, remains the same throughout. Just to show that the copper went in throughout, which was nice. And so this is just the last result. And I just very briefly would like to say that what you have to see, because these are very busy graphs. And actually, I realized that I'm making a master class of how you shouldn't give a talk. The younger researchers, so don't show so many results in such short space of time. But I want to exemplify a little bit of the ideas, that the range of work we think we can do in the interface between enzymes and metal organic frameworks. But coming back to this result, is here the point is that what you can see that when we're starting from the MOF, so we first reduce the copper just to make sure that it is in copper 1 state. And then we activate oxygen, so we flow oxygen through it. So there the copper gets oxidized into copper 2, the oxygen gets activated, and then the oxygen can react with the methane, which is then flown through it. And then here the copper gets re-reduced. So this means that the xylyl framework is actually has the potential to act as a methane reducing catalyst, or a partial, methane oxidation catalyst. So with that, I would just like to conclude. I've put some words up here, but MOFs are, I think, a very exciting and interesting system in order to translate enzymes into man-made synthetic products. And I hope I showed that some of these copper-based catalysts are active for CH activation. And then there is room for improvement, but also there is, well, maybe enthusiasm, even though I haven't necessarily displayed that in our group to do that. So thank you very much for your attention. Thank you.
Great talk. I was wondering if you look at the electrochemical activity of any of this copper-containing species, because you showed very nicely that they can undergo oxidations.
Yeah, so we are looking at that a little bit. So we have started to do some cyclic photometry to check if we can activate them. So at the moment, of course, we're a bit limited by the fact that these MOFs are very insulating. So we're not confident that we actually reach all the copper throughout the system, but we do see some activity, yes.
Take the time, we really have to move on. So join me to thank the speaker again. And before you go, before the coffee break, and on behalf of the organizers of this event, I think we're going to call the sponsors of this conference to join me here, and so that we can acknowledge their support. Are they in? Or just either come here or stand up as you wish. Please. You have seen that they have a stand outside, so please go talk to them because they're also an important part of all the conferences. Thank you very much.
Okay, okay. Bueno, bueno, bueno. Uno, dos, tres, probando.
Hello, everyone. We'll get started with the afternoon session. And we have our career perspective for industry and patent law. So today we will have three speakers. I'll introduce them briefly, mention the company, and then let them introduce themselves as well. So participants, we have Katerina Volt for micrometrics, Annette Condor from Surface Measurement Systems, and Carlos Wolfolk from, sorry if I mispronounced it. All right, so with that, I'll pass it to them. I'll pass the microphone.
So good afternoon, everybody, and thank you for the introduction. I'm from Surface Measurement Systems, and I'm the IGC product manager at the company. The company is dedicated on sorption science, and throughout the day and yesterday, you could see our stand outside. And if you have any questions, please do not hesitate to contact with us. And we are happy to answer any of your questions and help you in any kind of analysis and questions if you have.
Thank you. My name is Katerina Volz. I'm from Micromeritics. You will see in the presentation that we give in a minute probably that we are part of Malvern Panalytical now. I'm here with my colleague Abel. Maybe you can show who you are, so you can also feel free to reach out to us. We don't have a booth, but we are available to discuss with you whatever you're interested in when it comes to testing of porous materials.
Well, good afternoon. My name is Carlos Wolfolk. I'm from here, from the Instituto de Materiales. I work in linkages or vinculación, linkages between university and industry. So my responsibility is to take the knowledge to the industry and make and valorizate all the knowledge that is created here at the Institute to make more, to increase the capability of share money from the market, no? So it's a pleasure to be here. Thank you for the organizers, and thank you for UNAM, and thank you for inviting me.
I'm just the moderator, so that's it. So as we agreed, are we going to start with the next presentation? So I think they have it there, right? Yeah, this is now.
I hope it's. I can improvise.
We have some technical difficulties. It's not turning on the.
I can
No
do
enciende,
some
¿verdad?
fun activity. Till we wait for the presentation, just a question. Anybody heard before about IGC? Inverse gas chromatography? system? Raise your hand. Let me know who's my groupies. Nice. Inverse gas chromatography. No? Okay. If you want to know the capability and the potential of the instrument, I'm happy to tell you everything about it, and I can talk about IGC. So quite a lot. Yeah, that's it. Thank you. So I'm from Surface Measurement Systems, and Surface Measurement Systems has a history with academia, because Darrell Williams, who founded the company, he was a research fellow at Imperial College when he established SMS. He was the first employee, and he was his own boss. And the first DVS instrument was basically his PhD thesis. It was kind of like an academic project. And since then, SMS growth, and today it has more than 100 staffs. And the first commercial activity was in 1991 when Darrell sold the first DVS instrument to Pfizer. And since then also, the company sold over 2,000 instruments all around the world. And later also, the company expanded the product range. So there's so many other products than DVS now available, all based on sorption science. And I hope some of the instrument sounds familiar for you, and use one of those to measure sorption capacity or specific surface area or other properties of your porous material. SMS also growth in the last 30 years. So there's different facilities all around the world. You can see on this map, there's 2 manufacturing sites, one in UK and the other is in the US, Allentown, Pennsylvania. And there's also different laboratories and subsidiaries in different countries. The relationship with academia remains strong, especially with Imperial College and with other academic institutes at SMS. Darrell Williams, who's now the managing director of the company, he's really passionate in research and very open for any kind of new innovative ideas. Currently, SMS actively collaborating with these institutes and universities on different projects. But SMS is always open to support academia and partnering in different grants, government funding. Also, some people doesn't know that SMS does also do a lot of research, and we are offering demonstration work for anybody who's interested in any of our products. And we also provide free sample analysis in case of any promising innovative research projects. And SMS is also has its own different awards. Recently, we had the Carbon Capture Innovative Prize last year. And this year, we partnered with the International Association for Carbon Capture. And we had award for an early to mid-career researcher. And now the researcher is at SMS, working with us and helping to develop a new groundbreaking instrument. Before I tell my story, how I transferred to industry from academia, because it's a conference about MOFs, I want to show you a quick study on MOFs. It's just 2 or 3 slides. And it was a very interesting study. It was MOFs polymer composite. And all of you know that the pore volume or the specific surface area of these materials are a very important property, a parameter. And in case of these composites, because this is combined with the polymer, to measure the specific surface area is not that easy. Using nitrogen sorption measurement, the surface area or the pore volume, what this group measured wasn't the expected surface area. And they did a deeper investigation, and it turned out because polymer has a low glass transition temperature, and when you measure the specific surface area with nitrogen sorption measurements, you expose the sample to a liquid nitrogen condition. So this composite is changing. So the polymer is going through glass transition, which affects the structure of the MOFs polymer composite. And they found out that using volumetric measurements at 0 degrees C and instead of nitrogen using CO2, or using gravimetric technique to measure the specific surface area, they can measure more reliable and more consistent surface area. Just the conclusion of this study is that I would not state any standard technique for any measurement, because it's always sample specific which technique it's gonna fit to your material. And inverse gas chromatography or DVS instrument can measure BET specific surface area at ambient condition, which is much closer to the application temperature. And also it will provide you a surface area, especially for sensitive materials. It's a more reliable compared to a very extreme condition, which is required for the nitrogen or the krypton sorption measurement. And talking with industry, routine analysis sometimes just done routinely and nobody think about what's the condition, what the sample might has to resist during the measurement. And sometimes they just do the measurements because they do it in the last 20, 30 years. But when they really go deeper in the measurements and they try to understand what's happening with the sample, they realize that what they measure is not really what they wanted to measure. And also because the material is changing. And yeah, there's so many factors what you should really consider when you do a measurement. And finally, just a couple of slides. I wanted to share my story. I studied in Hungary at the University of Pannonia, where I received my master's degree in chemical engineering, and then I did my PhD in physical chemistry. I joined to a research group at the Department of Physical Chemistry in 2004 for the purpose of learning more and experience more besides the laboratory classes. And I joined to a very interesting project which was supported by Givaudan. I don't know, maybe you heard about this company, but this company making fragrance and flavors. And this is one of the biggest company who's specialized for these materials. And during my PhD, I had an opportunity to spend half a year in Switzerland at Givaudan and to experience everything at an industrial level. I really loved working with fragrances and also using IGC. And I was really impressed how versatile is this technique. But this time I was not aware that SMS also developing IGC. We always used our home built IGC system. And in 2011, the research group I was working purchased the first IGC from SMS. And then we attended at SMS conference in Paris, where I had the opportunity to meet with Daryl and with other people at SMS. And soon after, I joined to SMS to really with the goal to fully exploit the potential of IGC in different industries. My advice for people, for researchers, that small conferences or symposiums are also worthy to attend, not just the big ones, the big names, or all these fancy conferences, all these small ones where you can create more meaningful connections. And be curious and open-minded. Don't be afraid to question and ask things, and take opportunities when it comes to your way, especially if it's in line with your goals. And also I want to share an inspirational quote from my favorite scientist, and not just because we share the same birthday, but she was really pioneering in women in science. She was a trailblazer, I guess. And my favorite quote is, since I was very young, is this, that we must believe that we are gifted for something, and that this thing, at whatever cost, must be attained. So thank you for your attention.
Thank you very much, Annette.
I just passed. Yeah.
Yeah, so we carry on with Katarina, please. Thank you. And where's each?
I don't want to miss the chance to thank the organizers as well. We have heard it from all the other speakers, but it's really such a joy to be here. And I was especially excited when I learned about this topic of this roundtable, because honestly, when I was a PhD student, I wish I would have had the chance of such a discussion and hearing from people that are already further in their career path. So that's what I hope I can give to you, a little insight on how the career perspectives from the micromeritics point of view could look like. So I will start with my personal career path, introduce the company and the possibilities that PhD scientists have within micromeritics a little bit, and I also brought some application examples. I graduated from the University of Hamburg. I studied chemistry, and under the supervision of Professor Fröber, I worked with metal organic frameworks, and my aim was to design and test MOFs for nitric oxide storage and release. And looking here, some pictures from about 10 years ago to get to the point where I could hand in my thesis, defended it. I think I don't tell anything new to the audience here, that it came with all sorts of emotions that can be summarized in this picture. We had those Hulk gloves in the group, and whoever needed them the most was allowed to wear them. So sometimes that helped making progress with our research as well. It was then in 2016 that I joined micromeritics. And at that point, I'd been looking for a job for roughly a year already. It was quite normal at that time. All my fellow PhD students searched 9 to 12 months. So it was not a big surprise, but it was also frustrating. I was lucky because I could stay in the group of Professor Fröber, worked with zeolites, hierarchical porous zeolites a little bit. And I remember it was in summer 2016 that he got a call from the back then manager of micromeritics in Germany. And this manager asked, is there anyone who finished the PhD thesis and will be open for a job? And I had no idea how working in industry would look like, to be honest, even though I had looked through all those open job positions. But what I knew is I didn't want to go to sales. Now, this position was a sales position. I started in sales for micromeritics for Northern Germany. This manager who called me was in sales as well. We had a first phone interview. He didn't use the word sales a single time. He could just sell the job to me perfectly because he explained to me it's about technical support and it's technical conversations you have with all sorts of lab managers. And I thought, yeah, well, sounds interesting. I give it a try. And he was right. It was not sales as I imagined sales would look like. It was fun. It was interesting. I learned a lot. But what I noticed is that what I liked the best is all the application support that I was also able to give. And therefore, I was very happy to get the chance to change to the application team, which was in 2019. I became part of the European application team. We only set that up back then. No application team existed in Europe before. And from there, I went to the senior application scientist position a couple of years later and started being in charge of the application lab that we have in Munich from the operational point of view. And it was this year that I was promoted to the application lab manager for the European lab. You see here a picture from the current team. It's not all of the team. We are right now still micromeritics in Germany, and altogether we are 13 people. 7 out of the 13 are women, so we are represented in this company. Looking at the company micromeritics now, I mentioned that we are part of Malvern Panalytical. They purchased us last year, and the branch or the micromeritics part brings expertise in surface area, porosity, density testing, or also everything related to catalyst testing. Some of you, I'm pretty confident, will recognize this instrument. Our 3-flex is our research gas adsorption instrument. When we now look at the aspect or the part that Malvern Panalytical brings in, the panalytical side is really specialized in particle size, shape, and particle concentration measurements. The panalytical side brings in XRD, XRF instrumentation. And this is one instrument that I'm pretty sure some of you know, the Empyrean, the floor standing XRD unit. And another part of the company is the SciAps group. They complement our portfolio by handheld instruments for elemental analysis. Looking at the history or story of micromeritics, we were founded in 1962. Back then, I think the word spin-up didn't exist yet, or startup, but it was a spin-off of the Georgia Tech University. And maybe you've wondered what the name micromeritics means. It's a word that originates from the Greek words for micro, small, and meros, particles. And it's in general a term that describes the technology and science of small particles. In the early 1900s, Professor Delaval at the Georgia Tech University was head of the department that looked into exactly this science and technology of small particles. He published a book that he called Micromeritics. And it was in 1962 then that Clyde and Warren Hendricks, two researchers from the University of Georgia, Georgia Tech University, worked with gas adsorption, with manual glass racked base instruments where every valve needed to be opened manually. And they were approached by industry and came to the conclusion that it would make sense to develop the first analyzer, it was called, the first commercially available, not fully automated, but at least slightly automated gas adsorption instrument. And this is where we had the first company building. Looking at the global footprint, then you see in red or purple where we have our headquarters and production sites. So the Panalytical office is in Almelo in the Netherlands, the Malvern one in the UK, and then in Norcross, still close to the Georgia Tech University, is where the micromeritics instruments are produced, and we have the headquarters here. You also see that wherever there is a green dot, we have direct offices or direct labs all over the globe, and we support customers as best as possible directly or working with dealers. If we think of the end markets or the different markets we support, to be honest, when I first started working with micromeritics, I was very surprised that gas absorption was used not only for porous materials. Somehow I had my little small world of porous materials. But if we look at this selection of end markets, whether it's the battery, carbon capture, or in general, clean tech market, or construction materials, pharmaceuticals, chemicals, metals, in all those areas, you find that particle or material testing is present, and you will find our instruments. And the vision of Malvern Panalytical is that we make the world cleaner, healthier, and more productive. That might sound like an empty phrase, but I think it is really the passion we have. And what one of my colleagues once said is, every day, each of us comes in contact with at least one product that at some point in its production journey was tested using a device from Micromeritics, Malvern Panalytical, or SciAps. And I think it's really true because looking at all those different markets, nearly everywhere material testing is of relevance. If we look at the youngest researcher we have in our lab, she has her career path still in front of her. What I tell her within Micromeritics or Malvern Panalytical, could a scientist with a PhD find his role? And the application team is the one where I'm still part of. I will say a little bit more about that in a minute. But then sales, you heard, that's where I started. In Europe, or at least Germany, more or less all salespeople have a PhD, scientific PhD, and it helps a lot because it's deep level conversations we have, and it's about finding the right solution for our customers. Then the market development team, we find a lot of PhDs there, R&D, of course, and also product management. This is the typical fields, not all of them, it's not a complete list, but here you find scientists. And then in general, within our company, we have two development routes. You could either go the expert way, become the expert of one technology or the expert of one market, or you go the manager route and you can implement more strategic skills within the science background that you bring. Talking about applications and the current role that I'm in charge of the European lab that we have in Munich. We have a small team there at the moment and support all our European customers. And this customer support would be training sessions or workshops that we give. It's also one-on-one support where customers might have questions regarding their measurements. They reach out to us, we help to understand, and we also help them to use the instruments in the best possible way. We do internal support by training internally our colleagues or support the sales team. We are also somehow the link between the customers and R&D or software engineering or the product management, because we are facing the customers. We know what the customers need. The person that's only in the R&D team might not know all the needs that the different labs bring with. And then another point would be the representation at conferences and trade shows. And something I enjoy the most probably is collaborations. Annette mentioned it. We have a similar philosophy at Micromeritics. We are in many collaboration with different research groups. We really love supporting science and academia. And whether it's testing materials or even developing new methods together with customers, it's a really important part of what we do. And two examples I want to share that result from such collaborations are now regarding physisorption. Looking at a standard nitrogen isotherm, this is something everyone with you is familiar with. We can get a BET surface area, pore volume. Sometimes, if we are lucky, we can also get information about pore size distribution. It's not straightforward with metal organic frameworks. There are not many models existing that match metal organic frameworks, so we really need to be lucky to find a model that fits. And in order to help here, a couple of years ago, we had a collaboration with the group of Professor Omar Faha from Northwestern University. And they synthesized a series of isoreticular MOFs, the NU series. You see the lattice here, it's the pushing the wrong button. The Kagome lattice consisting of larger hexagonal and smaller trigonal channels. And one of my colleagues, Jacek Jagiello, he developed using these series of MOFs, he developed the very first metal organic framework kernel based on argon as adsorptive and the cylindrical pore geometry that came closest to what we see here. And this was a very nice collaboration that helped to get more information about the pore size of these materials. We could go even further. This is another example now looking at zeolites, where those zeolites from the group of Professor Perez Ramirez from ETH in Zurich wanted to use zeolites coming with microporosity for a catalytic reaction. So they needed to implement larger pores to guarantee the product mass transfer. And this is just a scheme of how they treated the starting material to implement mesopores. And what was interesting or important for them to understand is how are the larger pores linked to the micropores. Looking at just the results from DFT or from BJH, we see that we still have micropores, a huge micropore peak. We see that we introduce mesopores to a different extent, but the question was how they are related or connected with one another. And here we could help by doing a scanning of the hysteresis of the mesoporous region, and by applying a differential hysteresis scanning approach, we could find out how the pores are connected. So you can create those 2D plots where we have the window side on the x-axis and the mesopore size, the cavity size on the y-axis. This is the starting material where we have only micropores. We don't see anything here, but then we can have different scenarios. We can have materials where a small pore of around 3 nanometers leads to mesopores between 8 and 12 nanometers. We can also have those open pores that are freely accessible and where there is no micropore or smaller pore blocking the larger cavity. So by this, I thank you for the attention, and it's a pleasure to be here.
Thank you very much.
Thank you very much, and very interesting, both companies and both careers and all that you have done. And I think they're an example for Mexico and Mexican companies and Mexican students and Mexican academy, because we need to put more technologies in the market. That's the reason, no? I am here because I am an economist, maybe the only economist here in the institute, no? I am an economist, yes. I studied economics, and my studies were about innovation, and then science and technology commercialization. And then that's why I'm here. I have been worked in the industry, looking for technologies in the industry, in the biotechnology industry. And then I worked in the politics, STI politics, science and technology politics, trying to make good programs for support the science and technology in Mexico. And there is a lot of things that I already saw in your careers that maybe in Mexico we should learn about how to get there, how to get to be a graduate or postgraduate student with a PhD that have that career in the industry. No, there is a gap here in Mexico between the academy and the industry, and people like me are trying to make that connection, because that connection have different gaps, no? And the gaps are not only in the policy, but in the university also. The university has been learning for about 10 years ago how to make the connection between the industry and the academy. On one side, all the PhD students are focused only on the science career and not on the market career. So maybe that gap, we should try to be looking how to get more specific to make from one place to another. So in this way, one of the ways are patents, for example, no? Patents are relevant for everybody because patent is the only way to make money with knowledge, maybe, but not all the time because power not always are not always the answer for make money for the students and the universities. So you should patent if you are going to commercialize your technology. If you should not patent. Patents are very expensive if you only make a patent and put it in the and put it in the keep it, no? On the wall. Yes, yeah, it's a very yeah. You need to be very have a strategy to make the patent go to the market because if you don't, it doesn't work. So the true value of knowledge is not only own it and create it, but share it, no? And share the knowledge makes you make money. You can valorize your knowledge if you share it with the market. If you only keep it, you are going not to make money with that. No? So in my career, I have seen that things in different ways and different companies, and maybe we should go direct to understand what are we making and where can we attend the needs. No? If we understand the needs of the market, we can make knowledge and science that should attend them, like you make with your companies and your career show. So maybe we should put more attention in those things. All the students should make more attention in this. The impact must be not only in the market, but social, to improve the lives of Mexican people, of the worldwide people. That should be the way to make science and knowledge in these ways. So knowledge should solve real problems, no? You should translate the knowledge in that kind of things, no? And maybe the path to make that is only to understand what are we making and why are we making it. So let's keep patenting, but let's keep connecting with the world, no? Let's keep writing articles, but connect with the problems. Because if we only make science to solve, I don't know why, I don't know what, it will be only a big knowledge thing, but not making an impact in that. It's important not also, and you say that in a way that we speak the business language, not only the science language. Maybe when we are scientists, we only speak in the way that the scientists understand, no? But there is a world in business that should not understand you, and the business and the science should be connected because it's the way we can create value for the university and for our persons. So we should understand both languages to make a good success things. The other way is we should return to society what the university and the government gave to you or give us. Huh? Because university and government invest in us to create knowledge and create science, and we should return it in a certain way. No? Because we have this purpose in the university to make knowledge and to make better persons, but also we should have impact in the society because we have a lot of things to do here, like students or like academics or like scientifics, but we are not always thinking how should I return that to the society or to the university that they are giving me the thing that I'm doing. So I recommend you to think about that. My work in the position I have, that is the linkages between university and the industry and the society, has a lot of responsibility because it's not easy in a society like ours to do that. No? So my position is to tell you that you should think about it, and that's why I'm here. And I think, I don't know if I create some controversies or not, but but I think it's important to have that in mind, because we are in the same boat, and we are in the same way, in the same universities, and in the same science position, and we should think about it, no? And maybe I will stop here and start asking some questions with here, and thank you very much.
Thank you. Okay. So do we have any questions from the audience? Okay, there, and then I'll go there. Is that okay? Okay, the microphone is coming. Okay, okay.
Thanks very much for your comments and your presentations. As you said before, for example, in the manufacturing countries, like is the case in Mexico, we have this gap, no, between the applied science and the academy. I mean, applied science like in the industry. So in most of the cases here, when you're trying to develop or you try to develop yourself in a research and investigation area, it's pretty difficult because, as you said, most of the processes are already established, and it's difficult that the clients would like to experiment something new. So with taking like into that in mind, I mean, I'm referring to the manufacturing countries. What perspectives would you have like to avoid this barrier, no, that we have like to be able to apply our knowledge into an industry that probably wouldn't like to develop that part, or that are already like very settled in what works?
I'm not expert here in the system. How is it working here in Mexico? But in Europe, it's a little bit different. The companies like also SMS, they are quite open to collaborate and for new ideas. And some of my colleagues in UK, they were at university when somehow they get in touch with SMS, and they had a very innovative idea to add to what we should add as a company to our product, how we should improve a specific product. And Daryl, or one of our senior manager, liked the idea, and soon later that person joined the company, started to develop that instrument at the company, and hopefully soon it's going to be on the market. So it's a little bit different in Europe, but I would highly recommend to, if you have an idea and you think it's something which could help for other people or for industry, or it has addings, just go and pitch it to the different persons or companies, and hope for the best. But it really is about connection and recognizing that something what you are doing or what you has in your mind, it has a value. Daryl was a research fellow when he kind of like developed the DVS instrument, and he established a company. He went for different industries, and one of them was interested in that product because water absorption or water wettability, it was quite important thing in the industry, but there was not really a automated instrument for. So it's hard, but you just try and don't give up. As also yesterday, the opening presentation, Susumu mentioned, yeah, don't give up.
Okay, thank you very much. We have another question here, a quick question. Thank you.
Hola, thank you so much for your talk. Recently, I'm moving around two different worlds, diffractometers and agriculture. And we contact some enterprises and mainly we found men in these meetings, no women. I'm the only woman in these meetings. So I don't know, how do you feel in your companies, the numbers, because we were talking about the numbers, Patricia, no? Catherine also, and many people talking today and yesterday. So how are the numbers in your company? Who are the leaders? Because you talk about men in your presentation, but I don't know, how is you feeling about that?
At SMS, the numbers are not that great. So we don't have that many women scientists at the moment, although they're all very supportive for women scientists. So I don't think that that's the reason. I don't know why, maybe because they think that, as you said, some positions, maybe it's like sales position is not what they want to do. But also I started as just an application scientist doing demonstration work. And I really wanted to, before I joined to SMS, wanted to do research, collaboration, some development. And it turned out after I joined that this is also part of my everyday thing to contribute to the development of the product. Yeah, so it's hard. It's a tough question, to be honest, because also I started as a scientist and then to move up and became a product manager. It wasn't easy, as I see for other male colleagues. Career path was a little bit much quicker than mine. And I don't know why, maybe they are not afraid to kind of like pitch whatever they think or want. I'm kind of like the person who's performing, and then sometimes, especially at the beginning, I was just hoping that they recognize my performance, but I realized that in industry, it's not how it works. Even if you are a good performer, you have to promote yourself. You have to always kind of like do a lot of self-management, and then they're gonna recognize. And still there's sometimes situations when a male colleague comes more in the view, but you just have to accept it. It's still a long way to be completely equal, as I feel, and just try not to take it personally. It's just it's really something which has been 100 years, and it's not going to change from one day to another. But yeah, don't give up. Yeah, that's also. And
yeah, maybe to add, when I started about 10 years ago, I was actually the very first woman in sales and direct sales for Micromeritics. And also, I remember back then the application team was 100% males or guys. So that is something that makes me optimistic to see what changed within the last 9 years, because now in Germany, for just the Micromeritics core team, not speaking about Malvern Panalytical as the larger organization in Germany, it's all the 3 salespeople are women. In the application team, the direct team would be 5 people. We have 1 colleague from Italy, Luca, the rest is girls again. So this change is something I could really witness during the last years. And I think we still have a way to go because especially if I look at the upper management within our company, it's dominated by male managers. That's still the case. I don't want to lie about that. We have a few women in really high management positions, but not too many. But looking at the scientific part, so if I look at the all over now Malvern Panalytical global application team, we're in total 170 people. I don't know the numbers, but if I look at meetings, then I would say it's half. So in this scientific field, we do see the women being present and contributing. And I hope we're going to change to have also upper management women
at higher level.
At higher
I agree,
levels.
absolutely. Yeah. Also at SMS, we have more female scientists than when I joined. When I joined, I was actually the only one, yeah. And since then, we also have more women scientists at SMS. But still a lot of yeah, male dominated. It's really hard, but yeah, hope it's gonna change. Yeah, but yeah, if you really like and this is what makes you joy, doing science and doing research. Don't get scared by all this male-dominated environment, or when you go for a meeting and there's just males and you are the only women. Yeah, just do it. Yeah, because sometimes, yeah, it's intimidating, especially when you go into a room and just males, and then you're the only women. And but yeah, it's also good to see the change. And
Okay,
we are
thank
here
you so
to
much.
help if you need any contact or any support. Yeah.
Okay, thank you very much. Thank you.
Okay, so we'll have next several oral presentations. Our first speaker is Professor Virginia Montiel Palma. She's from Mississippi State University, and she will tell us about organometallic complexes on MOF support, harnessing synergy for robust catalytic platforms.
Muchas gracias. Ahorita, aquí. Okay. Ay, pero debe ser regresar este. Ah. Ujú. Ya me presentaron. No, la anterior. Sí, aquí está. Está bien. Perfecto. Sí, excelente. Muchas gracias. Well, thank you so much for the introduction. Really, it's an honor to be here with you today. I'm really enjoying this conference, and for me personally, it's really a privilege to come back to my alma mater, UNAM. So for all these reasons, I'm extremely grateful to the entire organizing committee for giving me this opportunity to present to you some of our most recent results regarding the heterogeneation or the attempts at heterogenizing our transition metal catalysts into solid supports, namely MOF materials. So my name is Vicky Montiel, and I work now at Mississippi State University. My background as a synthetic organometallic chemist has allowed me to propose, or has our group allowed to propose, has allowed our group to propose the synthesis or access of phosphorus containing ligands modified with a group 14 element. And namely in this talk, I will concentrate on silicon, but of course the rest of the group 14 elements are known for their important electronic properties, namely their very strong sigma donation that causes the ligands in which they make part of to perhaps modify the kinetics and normally have some advantageous effects in catalysis. And today I will concentrate on the chemistry of rhodium and iridium. Okay, so some years ago, we reported the reactivity of this potentially tridentate bisilylphosphine ligand. Please notice that there is a semi-rigid functionality between the phosphorus and the silicon. And the reactivity of this type of ligands towards two of the most common iridium-1 and rhodium-1 sources, namely the chlorocyclooctadiene dimers, is pretty straightforward, giving rise to the substitution of the cyclooctadiene ligand by the phosphinosilal-1. These dimeric structures characterized by a variety of spectroscopic techniques, but namely here, X-ray diffraction structures show a typical square planar geometry around the metal center. Please notice that the metal is in oxidation state 3 and is formally a 16 electron species. Now, if we now employ the isopropyl substituted instead of the methyl substituted ligand and reacted in the same type of reaction, we now obtain monomeric species of this type in which the metal center, rhodium or iridium, is tetra-coordinated. You can see here. And the angles around, well, silicon, metal silicon angles are around 100, if this appears here, yes, are 100 degrees. You know what? I'm hating that pointer. I will use this one. That's much better. So the angles around the metal and the silicons are rather acute, about 100 degrees, whereas the phosphorus metal chloride angles are approaching linearity. And so actually we characterize these compounds. We have a lot of fun utilizing a lot of spectroscopic techniques. And here I couldn't resist to show you the 29 silicon proton decoupled NMR spectrum of the rhodium species, which shows a single resonance for the two magnetically equivalent silicon nuclei, but it appears as a doublet of doublet due to the coupling with the phosphorus and the rhodium nuclei. Anyway, now please notice that in this last case, we have formally a metal in oxidation state 3 and with 14 electron count. Okay, and if we apply a simple formula with the geometric parameters, we realize that the geometry of these complexes is an unusual seesaw structure. Therefore, having a 14 electron species with a sawhorse geometry prompted us to think that its coordinatively unsaturated species must be very active for several transformations. Okay, so actually in the literature, there are only a handful of 14 electron, very unsaturated species of this type. Most of them are stabilized by agostic interactions of this type, or maybe by the presence of oxygen, which bears non-bonding electrons, which also stabilize the metal center. In our case, we find no evidence of agostic of this type, agostic interactions in our complexes, and we attribute the stabilization of these 14 electron species to the sigma electronic properties of the silicon atoms. Anyway, so we wanted to use these complexes to catalyze reactions in which we could functionalize unsaturated organic bonds with silicon. And as you must be aware, hydrosylation is one of those reactions that are very important in industry, with many of the products making their way to our everyday life in the form of polymers, in the form of fine chemicals, pharmaceuticals, etc. But we particularly wanted to preserve, see, I go back to that one, to preserve the unsaturation while including silicon. I also want to notice that besides this dehydrogenative silyllation reaction, we are also interested in the functionalization of internal alkenes, for which there are a lot less catalysts than for hydrosilylation. And at the same time, the functionalization of these internal alkenes could also lead to the called tandem isomerization dehydrogenative silyllation. So indeed, we use our complex, our 14 electron complexes for this type of reaction. And we noticed that when we employ the rhodium complex, we could access selectively the hydrosilylation products of styrene and of internal and terminal alkenes. And when we employ the iridium catalyst, we could access the dehydrogenative silyllation products. So far so good. Our tones are relatively low, 100, but are pretty good for this type of transformation. So now our next step is trying to make our catalysts more useful for industry. So one of the options is trying to heterogenize them. So we thought about using different types of support materials. Namely, today I'm talking about polymers and also MOF materials. And since this is the goal of our conference, I just want to stress that this type of very excited, beautiful architectures can, of course, serve on their own right as catalysts, but we wanted to employ them as catalyst supports. And we chose to use the method of post-synthetic grafting and employ this MOF material, which has been mentioned a few times today, first synthesized by Professor Farha at Northwestern, and which is a mesoporous type material with a pore relatively large and able to accommodate a relatively large transition metal complexes. It consists of pyrene linkers and a zirconium node that bears hydroxyl terminal groups where we can anchor our transition metal catalyst. Okay, and so our approach, well, we attempted several ways of grafting our organometallic precursors, but we found that alkylation towards the formation of a methyl derivative and then a reaction with a MOF at room temperature could lead to the incorporation of a small amount of the iridium complex in the zirconium nodes. And we were able to characterize the methane that is extruded from this reaction by IR spectroscopy and to confirm that in the final product, we still have the iridium in oxidation state 3. Actually, with Professor Ibarra, we carried out some, well, they carried out some studies with gas absorption, which show the material to be very robust. So if it was very robust for the absorption of sulfur dioxide, it was also very robust to catalyze our desired transformation. And indeed, we can recycle this catalyst a few times. We obtain majorly the dehydrogenative silyllation product, preserving the unsaturation. However, we obtain still a little bit of the hydrosilylation product. Okay, the other advantage is that now we have an air stable system and we have increased the tone for about an order of magnitude. And the system tolerates a variety of functional groups in the styrenes, for example, and as I said, is amenable to be handled under air. Okay, so now when we attempted to functionalize or to also graft the rhodium analog in the same fashion into the same MOF material, we actually found the problem of accessibility to the methyl derivative. So now it is not possible to obtain the methyl derivative, or it actually is, but what happens is a reaction in which this methyl now migrates to the silicon, and effectively the ligand is now decomposing by forming a new rhodium methylene bond. So we resorted to going through another pathway, which is actually the direct lithiation of the MOF material, and then reaction with the chlororhodium derivative to finally obtain the grafted rhodium MOF. And we were able to characterize this material exhaustively. Basically, again, X-ray absorption spectroscopy allow us to confirm the oxidation state 3 of the rhodium, and X-abs as well, the presence of a rhodium oxygen bond. And the same thing when we try this material as catalyst, we are able to handle it under air, and consecutive reactions in which we can recycle it show no loss of the catalytic activity even after several cycles. Now, most importantly, we do not observe any hydrosylation product and only a small amount of the hydrogenated byproduct, which is easily removed. I'll try to go a little bit faster. We try to understand the mechanism by which these materials work, and for that, we look at performing stoichiometric reactions of the precursors, the organometallic precursors, and we found that unlike most of the catalysts for this type of transformations, we can never access the rhodium hydride or the rhodium silyl derivatives, even in the presence of a very large excess of the triethylsilane. However, when we employ styrene, for example, we do observe a formation of an adduct, which I am going to talk later. So just in the interest of time, I'm going to just let you know that actually these systems is pretty interesting because some unusual transformations take place. For example, the isomerization of one of these isopropyl substituents on silicon leading to this N-propyl product is actually quite linked to the mechanism in which, for which we are trying to study. We determine also the kinetics of these systems and found an order on the catalyst, a fractionary order of about 0.5. And we also found an order on the styrene of 1.5 at 0 for the silane. So with this and other studies, including computations by my friend and colleague, Oscar Jimenez-Aya, we propose that the catalyst undergoes a pre-equilibrium forming this species, which is actually trapped by styrene, explaining the higher order on styrene and the lower order on the rhodium. Rapid oxidative addition of triethylsilane leads to the 0 order determination of the triethylsilane, and then finally, this is our proposed mechanism. So just very quickly, in the next 2 minutes, I want to tell you a little bit about another support that we have explored. Again, with our collaborator, Sam Dunning, now at the University of the District of Columbia. So now he is able to polymerize, effectively polymerize aromatic organic molecules by subjecting them to a really great pressure of the order of gigapascals. And so in an analogous way to what happens to carbon converting to diamond, they can also obtain polymers of these organic molecules. And so we use one of them, this furane derivative with a carboxylic functionality. And we also use it to graft our iridium materials. And we propose first the deprotonation of the polymeric material, followed by the reaction with the halide. And again, we use it for the catalytic reaction we are interested in, and found that we can recycle the material a few times, and the material is very selective again for the selective formation of the dehydrogenative silylation product. We explore another material, for example, this polymeric pyrazine derivative. In this case, we use a different organometallic approach by which we remove a hydrogen by lithiation and then the reaction with the chloroiridium compound. So in this case, actually what happens is there seem to be polymeric chains of smaller molecular weight, and therefore we are able to sometimes follow by NMR spectroscopy, namely lithium-7. And we can also obtain selectively the dehydrogenative silylation product using a variety of styrenes. However, in this case, there's a small decrease in the catalytic activity after 9 cycles. However, when we confirm the oxidation state of these materials in both polymers, the furane, the furoic derivative and the pyrazine derivative, we also observe or confirm the oxidation state 3 in the on the iridium. And in exapts, we propose also the presence of iridium oxygen or iridium carbon bonds. So I'm sorry that I have been too fast, maybe in trying to give a lot of information, but I think our conclusions to date is that we are able to heterogenize our organometallic complexes by grafting them onto MOF materials or polymeric materials. And in most cases, the catalytic activity is enhanced. And now the materials are more robust, and we're able to recycle them a few times without significant loss, except in the last case, of catalytic activities. And we attribute this to the matrix isolation effect that happens when we host these organometallic precursors into the MOF materials in particular. And with that, I just want to take a minute to thank the people who have made this work possible, which is my research group, of which I am extremely proud. And I am noticing some similarities with, I believe, all of the presentations that we have had previously. So basically, we are not a very diverse group, as you can tell. This is my current group. And I'm also extremely grateful to my collaborators at different institutions, particularly most recently, Dr. Chen at Argonne National Lab, who has allowed us access to synchrotron-based techniques, and of course to Sam Donin, Argel, and Oscar Jimenez. Also my previous collaborators in France, where I started the homogeneous work. And I should also be grateful for the start of my career in my home country, Mexico, and the support of then CONACYT, and also Mississippi State University and the National Science Foundation for sponsoring this work. Thank you for your very kind attention. I would be very happy to answer any questions. And I normally keep my acknowledgements very professional, but since this is a very, very special conference, I wanted to show you a couple of pictures of my family, to which I am also very grateful. So 14 or 15 years difference. Thank you. Thank you for your kind attention.
Questions for our speaker?
Thank you for the beautiful talk. I have a question about your nanothreads.
Yes,
How long are they? And can you control like the density of functionalization with your catalyst on the thread?
Yes, well, how long they are, we have some ideas, and we more or less can tell. I mean, we know what is the metal content on them, so we know that we must have alternate functionalities, especially the carboxylate iridium, but we're not absolutely certain about the rest of the characterization for those materials. So my answer is partial to your question. We're still on the way to performing more characterization of this species.
But can you consistently control like the loading of the catalyst?
Yes, yes, we can. We can include a lot less catalyst or a little more of that. Okay. Yes, we can. Thank you for your question.
Any other questions?
Thank you very much for your presentation. I just got a quick question. How does these functionalizations affect the porosity of the materials that you work with?
Okay. Yeah, well, we incorporate these transition metal fragments in a very small amount. So I believe some of the materials that I presented, the iridium ones at the beginning, are present in only 0.5 weight percent. And in fact, we have only one, I have to go to the beginning, but we have only one iridium per 11 zirconium-6 centers. So it's actually very low metal loading. So we still have a pretty high surface area in the materials. I mean, it has decreased, but it is pretty high still. Yes, thank you.
Thank you very much.
Yes,
Any other questions?
The other way around.
I had a question about the degradation pathway. Maybe could you comment about
Say again?
the degradation, right? You show that the catalytic activity decreases over 8 cycles.
Yes.
I was wondering if you can comment on that.
Yes, I can. So what happens is that these polymeric materials are normally insoluble, and obviously because they have a really high molecular weight. But there must be during the synthesis some polymers that have a much lower molecular weight, and they are the ones that we are able. I just want to show you that we are able to characterize some of these materials, for example, by lithium-7, and those must be those chains with smaller molecular weight. And so what must be happening is because the process of catalysis, then we filter and recover it. Some of these polymers are soluble, and so we're losing some of the catalyst because of the way we are recovering our catalyst. So I guess if we were just able, or if we were just to evaporate the solvent, we would still have the same amount of metal catalyst, and therefore we would not have any decrease in the catalytic activity. But because we filter it and some of these chains are soluble, then we decrease some of the catalytic activity. Thank you.
If there are no further questions, please join me in thanking our speaker one more time. Our next speaker is Aya Mita from Kyoto University in Japan, and she will tell us about one-dimensional self-assembly of metal organic octahedral towards mechanically flexible microporous aerogels.
Sorry, can I have a slight moment? Thank you very much for waiting for me. I'll start my presentation. Thank you very much for the kind introduction. So today I'm talking about, sorry, the size is a little smaller. Is it okay to continue? So sorry. Yeah, I'll talk about one-dimensional self-assembly of metal organic polyhedra towards microporous fuels and its resulting emerging mechanical flexibility. So yeah, to begin with, I would like to think about the relationship between the internal structure and mechanical flexibility within the functional materials. So as discussed in the morning session, the diamond and carbon nanotubes are both composed of carbon atoms. However, the carbon atoms are connected in a totally different way. So the diamond has a three-dimensional network of sp3 bonding. And on the other hand, carbon nanotubes has sp2 bonded carbon sheets rolled up into one-dimensional tubular structures. And when these structures are subjected to a mechanical stress, such as compression, diamond fractures without any deformation, while carbon nanotubes can deform flexibly in response to the external stimuli. So in this way, the three-dimensional network structure such as diamond is rigid but tend to be brittle, while low-dimensional structures such as carbon nanotubes are advantageous for stress dissipation. So yeah, so these kind of principles are widely seen not only in these carbon allotropes, but also can be seen in polymer science or molecular crystals or protein crystal or our friends porous materials. So as you all know, the noble porous materials such as synthetic zeolite and metal-organic polyhedra, metal-organic frameworks have covalent or coordination bond-based network structure, and due to their well-ordered molecular arrangement, these materials are often synthesized as hard crystals. So according to the previous studies, the Young's modulus of which represent stiffness result ranged from 3 gigapascals to a few gigapascals to 100 gigapascals. And this indicates that these porous materials are as stiff or more stiff than thick balls, which are typically used for the flow links. On the other hand, despite their hardness, these materials are quite brittle. So to illustrate this, we took a look at the value known as fracture strain. So these represent how much a material can be compressed before the cracking occurs. So the higher values indicates a greater mechanical flexibility. So for instance, ductile metals like a copper plate shows at least 30% of the fracture strain. However, synthetic zeolite and metal-organic frameworks shows only less than 0.1%, which are categorized as highly brittle materials. So for their practical application, it is essential that these mechanical brittleness be improved. So yeah, therefore in this work, we aim to synthesize mechanically flexible microporous materials. And to achieve that, we focused on utilizing weaker intermolecular interactions rather than strong covalent or coordination bond, and also to introduce lower dimensional structures. So in concrete, here we employed metal-organic polyhedra, MOFs, as porous building units. And this hollow and discrete molecule is composed of metal ions and organic linkers. And by assembling them in a one-dimensional manner using a van der Waals interaction, we aim to make new types of porous materials with enhanced mechanical flexibility. So we selected an octahedral molecules with copper paddle wheel and naphthalene diamide derivative linkers. So due to this NDI plane exposed on the surface, exposed on the outward, this MOF has a large molecular surface. And also throughout the condensation reaction, we can introduce several amino acids with their side chain exposed on the surface. So the combination of this NDI plane and amino acid side chain makes it easy to adjust the intermolecular interaction between MOFs. So indeed, our group has recently demonstrated that the these NDI MOFs with phenylalanine and alanine groups assembled three-dimensionally and resulted in highly rigid van der Waals frameworks. So in this work, by controlling the surface structure and their assembly, we successfully made a mechanically flexible microporous aerogel, which I'm going to represent today. So the NDI linkers were synthesized by reacting the naphthalene tetracarboxylic dianhydride with L-isoleucine under basic condition. And this linker was further mixed with copper nitrate trihydrate and heating at 80 degrees for 24 hours, resulting in 2.7 nanometer sized octahedral molecules. So in the following section, we assemble the molecules. So since the weak intermolecular interactions are highly affected by the solvent condition, so the solvent selection is very important to achieve the desired molecular assembly. So here, in order to achieve the desired MOP assembly, we purified the MOP crystals and prepared MOP solutions. And into this solution, we added 21 different types of pore solvents to see which kind of MOP packing they would induce. So as a result, 3 distinct cases were observed. So when we used these top solvents, the octahedral crystal OC was obtained directly after the addition of pore solvents. But on the other hand, however, in the case B, after the addition of pore solvents, the viscosity of the solution was increased and it finally formed a self-holding gel. And this gel seemed to be in a metastable phase and it was finally transformed into a hexagonal pillar-shaped crystal HC. And in the case C, no precipitation was observed even after the addition. And in the following section, we conducted a single crystal X-ray diffraction measurement on these 2 crystals. And as a result, in the crystal OC, octahedral MOP structure was observed. And here, the neighboring MOPs were interacting through their amino acid side chain and had a relatively large empty space between them. And here, electron density was observed, suggesting the presence of disordered solvent molecules in between. And also the distance between the inter-MOP centroid, the centroid of the MOPs, were around 27 angstroms. And octahedron has 12 edges. So as a result of these inter-MOP interactions, these MOPs were isotropically packed into a face-centered cubic lattice. And in the crystal HC, the same octahedral MOP structure was observed. However, the interaction and packing were totally different. So here, the MOP molecules was interacting through their NDI planes and amino acid side chains. And the distance between the centroid of MOP molecules were around 22 angstroms, and which was much shorter than that of crystal OC. And for these inter-MOP interactions, 2 phases of the octahedrons were used. And as a result of these further assembly, these MOP molecules were forming a helical chain-like structures. So here we focused on the vertex, which was represented in a red point. So when we trace them along this chain, the MOP molecules were rotating around 120 degrees per 6 MOPs. And if we borrow the biological terminology, the 1 pitch will be 40 nanometers and the rotation per unit will be 20 degrees. And within their large unit cell, many chains assembled together. And as a result, the molecules were packed in a highly anisotropic manner. And to understand their interaction between MOPs, we extracted 2 NDI linkers between neighboring MOPs and conducted energy decomposition analysis based on the DFT calculations. So as a result, crystal HC showed a twice larger stabilization energy. And in both cases, the dispersion forces was around contributing around 90% of the total stabilization energy, which clarifies the inter-MOP interactions are based on the van der Waals interactions. And in order to understand the solvent effect on MOP assembly, here we took a look at the Hansen solubility parameters. So these 2 parameters in the X and Y axis quantifies the interaction strengths corresponding to London dispersion and dipole-dipole interactions among all the intermolecular interactions. So using the literature values, we calculated the solubility parameters for each conditions and plotted them as shown here. And when we reflect these 3 results on this plot, we realize that the 1-step crystallization in case A occurs when we use a solvent with strong dispersion forces or lower polarity. And the gel-mediated crystallization in case B occurs when we use the solvent with weak dispersion forces and higher polarity. So from this analysis, we try to understand or interpret the solvent effect on MOP assembly. And we hypothesized that the addition of low polar or strongly dispersive solvents induce MOP solvent interactions, resulting in cocktailization into isotropic packing. And on the other hand, highly polar and weakly dispersive solvents induce rapid intermop interactions, leading to a metastable gel phase and resulting in anisotropic assembly. So since the anisotropically packed crystals were still rigid, we focused on the kinetically obtained gel phase in the following section. So due to the non-covalent interaction between MOPs, this gel showed a reversible Solger transition in response to the external stimuli. And thanks to this reversibility, we could shape this original gel into several forms, such as flowers or stars. And in order to use this gel as a porous materials, we have to remove the remaining solvents. So utilizing a supercritical CO2 dryer, we remove the remaining solvents and obtained a corresponding L gel. And as seen in this SEM micrograph, the L gel showed anisotropic nanofibers entangling together. And we defined the fiber width as shown here and measure 200 points for this micrograph and realized that the average width was around 15 nanometers. And when we consider the diameter of molecules is around 2.7 nanometers, this fiber width corresponds to 5 to 6 molecules. And also we had an opportunity to measure cryo-TM measurement on these fibers. And as seen this one, this micrograph, the fiber width was consistent with the SEM observation. And furthermore, we could see some dotty patterns in the right side micrograph. And when we did the Fourier transformation of these dotty patterns, we figured out the corresponding domain spacing was around 2.5 nanometers, which is approximately equal to the diameter of one molecules. So to evaluate their porosity, we conducted a nitrogen adsorption measurement on these 3 samples. And the result showed, L-gel showed a high gas uptake at low pressure, indicating the presence of microporosity originating from the MOP's intrinsic pores. And finally, the mechanical flexibility was tested using uniaxial compression measurements. And as shown in this stress strain curve, the elastic deformation was observed until the strain value of 27%. Sorry. And the Young's modulus at this region was around 41 kilopascals. And after the yielding point, the L-gel showed plastic deformation. However, even compressed up to 85%, we could not see any fracture point, which suggests that L-gel have a high mechanical flexibility compared to other porous materials. So in conclusion, we identified the appropriate condition to assemble the molecules into one-dimensional nanofibers. And by further processing them into L-gel form, we could combine both microporosity and mechanical flexibility. And finally, I thank all of my group members. Actually, as you can see, we are working in a quite diverse environment. And also I thank our collaborators who helped for my work. Thank you very much for your kind attention and for your patience.
Thank you very much. It's fascinating how you modulate the chemistry by changing the solvent. Have you thought about adding, for example, a support to modulate the growth of these fibers with some shapes or?
Thank you very much. we try to we try to see if we can control the thickness by using sonicator, for instance, but we didn't try any modulator to manipulate their assemblies. But we would like to try. It's gonna be a nice trial. Thank you very much.
Any further questions? Yes.
Thank you for the beautiful talk. I'm wondering if you have used for the alcohol solvents for the isotropic assembly, have you used polyols instead of ethanol or methanol? Polyols with multiple alcohol.
That's true. We didn't try. Absolutely, this system has a tendency that if you introduce a polar groups, it will, introduce or promote anisotropic packing. But yeah, we didn't try like several OH group polyols, but it can be interesting. But sorry,
that's it. We can discuss later.
Yeah, thank you very much.
Another question?
Wonderful talk. Thank you so much. I was wondering about the intrinsic porosity. I was very surprised, but of course you would correct me. But it looked like the intrinsic porosity was actually microscopic. It wasn't like mesoscopic or mesoporous. Is that right? Is it?
Yeah, MOFs, the metal polyhedron has a microporosity, and this, yeah, it has a microporosity, but no mesoporosity.
That's super interesting because normally the intrinsic porosity can be anything. And it's normally microporous or mesoporous or anything random. And I think that's due to the stability of your systems and the very strong interaction between the cages. Is that right?
You mean to demonstrate a microporosity?
Well, you already demonstrated, but I was trying to understand that's because the forces between the cages, and that's the case that it creates only microporosity.
Yeah, absolutely. So to be in a van der Waals systems, surprisingly, it could stand for the supercritical CO2 drying, and yeah, thanks to the strong interaction between the MOFs to form fibers, it could maintain the structure to exhibit its microporosity. If it's amorphous or if it's totally losing the long range order, even though there is a MOF, yeah, as you expected, no microporosity will be seen in the isotherm.
Thank you very much. Very nice
Thank you very
talk.
much.
Thank you.
If there are no further questions, please join me in thanking our seminar speaker one more time. Her name is Yuri. Oh, okay.
Don't worry.
Hello, good afternoon. My name is Eric Uribe. I am actually a PhD student at Institute of Chemistry here in UNAM, and I am actually working on the functionalization of wheel-type metal-organic frameworks. And I would like to share with you a part of my research focus on using multi-component reactions to create new functionalized materials. In a traditional organic synthesis, usually we use many reaction steps which take a lot of time and energy. Because of this, recently we developed new methods to have a better opportunity to synthesize new molecules. One of the most useful are multi-component reactions, which take these reactions in only one flask and use generally 3 or more static materials. One good example of these multi-component reactions is the Ugi 4-component reaction, where an amine, a aldehyde, a carboxylic acid, and an isocyanate react to form alpha-acyl aminoamides. This reaction is very versatile and can even use to obtain new materials such as MOF. In this project, we started with the synthesis of a biphenyl compound containing an amino group. This was achieved first through a nitration reaction, followed by a reduction step. We then use this compound in the Ugi reaction with different aromatic and aliphatic aldehydes and also different carboxylic acids, keeping the terbutyl isocyanate fixed in the reaction. As a product of this, we obtain 5 Ugi adducts with different functional groups. Next, we perform a basic hydrolysis with sodium hydroxide to obtain the organic ligand containing the carboxylic acid. When chloroacetic acid was used in the multi-component reaction, we also obtain the ketopiperazine derivatives with the product. All these ligands were characterized by proton and carbon, These ligands were also characterized by proton and carbon NMR, infrared spectroscopy, and high resolution mass spectroscopy. Next, these ligands were used to synthesize MOFs through solvothermal synthesis using DMF as solvent and zirconium tetrachloride as the metal source. PIXRD patterns show reflections that match those of WIO67, confirm that these compounds are isostructural to this material. Next, thermogravimetric analysis also show to these materials are less thermally stable than pure WIO67 due to the loss of the incorporated functional groups. Finally, with solid state carbon NMR, confirm the incorporation of the Ugi adducts by the signal of the terbutyl group at 26 parts per million. We also prepare MTB MOFs by mixing 50% of the organic ligands and 50% of the biphenyl compound. The PIXRD were sharper and more intense, meaning these materials are more crystalline. Also with thermogravimetric analysis show a higher stability. And finally, with solid state carbon NMR confirm the incorporation of the functional groups by the signal located at 26 parts per million. Okay, very recently this semester, we test a modified version using the 3-component reaction, which includes an amine, a aldehyde, and isocyanate. In this case, we use phosphoric acid instead of carboxylic acid to help protonate the imine in the mechanism reaction. After the basic hydrolysis, also we use this new ligand to the synthesis of the functionalized MOF. PIXRD also confirmed the WIO67 structure. And as we obtain this pattern, also show a better crystallinity than the previous series using the full component reaction. And finally, we also made its MTV MOF, and we also obtained the same three-dimensional structure as the past materials. Finally, as additional comments, the results show that the UGI-derived ligands can be successfully integrated into the WIO67 without losing its structure or crystallinity. The introduction of functional groups allows us to tune the chemical environment and potential application of the MOFs. This approach proves that the multi-component reactions are an efficient strategy to design whole families of functionalized isoreticular MOFs. Overall, this work opens new possibilities for creating MOFs with customizable functionalities through a simple and versatile chemistry. I want to thank to the Congress Organizing Committee for the opportunity to present this work. And also, I want to thank to the amazing women of our research group and all the technical academies for the contribution of the analysis. And thank you so much for your attention.
Thank you very much, Eric, for the nice talk. I wonder, did you, maybe looking at the 100% functionalized linker MOFs, did you maybe evaluate, or are you planning to evaluate the missing linker defects? Because the structure is quite prone to this. And I think it may be interesting to see if there is a correlation between the chemistry of the linkers and the defectivity they cause. If I may, so that tells you that all the linkers are your functionalized linkers, so they didn't decompose, but that doesn't mean that there are no missing linkers. So maybe combining the TGA with some post-digestion NMR or something like this could be interesting to explore the defectivity. Yeah? Well, thank you very much.
Any additional questions? All right, if not, let's thank our speaker one more time. Sorry. Our next speaker is Erika Medel from Universidad Autónoma Metropolitana Iztapalapa. And she will tell us about a computational approach for non-covalent interaction in MOFs and guest MOFs systems, the case of the manganese OLZ, which she will tell us about what it stands for. Okay.
Thank you. Hi, good afternoon, everybody. My name is Erika Medel, and I go to talk about a computational study of non-covalent interaction in MOFs, especially of MG2 OLC, where OLC means oxalate. Okay. What is the relevance of non-covalent interactions? Well, these interactions, although weaker covalent bonds, are crucial for cohesion and stability for different systems, including MOFs. Understanding this interaction is very essential, or is essential, not only for pristine structures, also for their applications. For example, for encapsulation of molecules within the MOF spores, for drug delivery systems. Studying these non-covalent interactions is very important because they govern the absorption and release of within the pores, the MOF spores. In this way, we study the encapsulation of phenethylamine. Phenethylamine. This is related with the function of the central nervous systems, and has been studied, experimentally studied as a guest in this MOF. In our study, we added derivatives of phenethylamine, which share an amino group. Regarding the methodology, we use density functional theory for periodic systems, and for analysis of non-covalent interaction, we use Cutein and NCI index. That is for analyze, we analyze the electron density to extract this information. And we use the Crystal software for compute the electron density, and JP1 code for analyze electron density. Okay, let's look at the results. First, we study the pristine MOFs. In figure 1, you can see the more stable geometry and not an open metal site. This is important for interaction with gas molecules. Using the NCI index, we determined the nature of different interaction. For example, the ionic interaction magnesium-nitrogen in open metal site. In the second graph, in these peaks that correspond to the weaker interactions, such as hydrogen bonds. Before this analysis, we added the molecules in the pores MOFs. The position of the molecules was chosen according to the experimental report near of open metal site. In table 1, we summarize the non-covalent interactions for each system. All interactions on conventional hydrogen bonds, hydrogen bonds, and interaction between heteroatoms, all related to with interaction energy. And this is related with the absorption and release molecule within the pores. This is true. This is especially true for interaction magnesium-nitrogen. That is the interaction with open metal site. Therefore, here you can see the electron density for these interactions and the magnesium-nitrogen distance. Depending of these factors, the interaction energy will be lower as with phentermine, or the interaction energy, or it will be more negative as with 2CB. It also depends the number of interactions. This is related 2 with the functional groups of each molecule. In table 2, I present the percentage contribution to interaction energy by the type of non-covalent interactions in each system. The interaction magnesium-nitrogen is the most outstanding. Meanwhile, the unconventional hydrogen bonds together also contribute with largest percentage to interaction energy, close to 50%. And we conclude that the proposed methodology allows the rank characterization of non-covalent interaction in gas MOF systems. The interaction energy is determined by specific functional groups present in each molecule and unconventional hydrogen bonds contributions. And these MOFs show promising picture for DDS. And thank you for your attention.
We're a little bit behind the schedule, so maybe one quick question, if we have one, and if possible, please ask it in Spanish. But if there are no questions, then let's thank our speaker one more time. Our next speaker will be Aida Guadalupe Velasco Ortiz from Instituto Politécnico Nacional, and will tell us about novel synthesis of ZIF-8 PPY nanocomposites to remove emerging contaminants in aqueous media.
Hello, my name is Aida Velasco. I am a bachelor's student for the Instituto Politécnico Nacional. Today I will present my project titled Novel Synthesis of ZIF-8 polypyrrole nanocomposites to remove emerging contaminants in aqueous media. So, as we know, water quality is a global challenge. A significant problem is the rise to the emerging contaminants. So in this project, we focus on two contaminants, that is code red. This is a toxic industrial dye in the ciprofloxacin. This is used to antibiotic. So as we see in the figure 3, we can see that this contaminant produce several risks, cause genotoxicity in aquatic life, and in humans cause many damage and other serious issues. So to address this problematic, we use an absorbent material. So first we synthesize the ZIF-8. This is a famous MOF because it has a high surface area and is a simple method to synthesize. So we only do 2 solutions and mix this to get the nanoparticulates. To these nanoparticulates, we use to do the nanocomposites. So we create a ZIF-8 polypyrrole. So after the synthesis of this material, the thing is that we perform an in situ polymerization of polypyrrole directly in the surface on the ZIF-8. Then we start to evaluate the absorption of this material in batch experiments. So we analyzing the effect of pH, the contact time, and the initial concentration of a contaminant. With the characterization, we use 3 different techniques to confirm the existence of ZIF-8 in the polypyrrole. So we did XRD. So we can see in ZIF-8 the structure is so crystalline, but when we add the polypyrrole, this crystalline gone. So this peak is gone, and we didn't see this crystalline And so this confirmed that this polypyrrole successful coating in the surface of the CIF8. So we confirm this with the FTIR spectrum. So we can see in the spectrum of the CIF8 polypyrrole, we can find the basis bands for CIF8, that is the orange, and we found at the same time the bands for the polypyrrole, that is the green bands. So to see how the morphology of these materials change, we did the same. So if we see the micrograph of CIF8, we can see that this is just a agglomerate. And when we had the polypyrrole, this change and it's like a flake-like structure. Then the results for the Congo red results, we did a spectrum. So we can see in the black line is the solution for the red Congo. And when we add the material that is CIF8 and CIF8 polypyrrole, we see that the nanocomposite has the most removal efficiency. So with this, we did a pH study, and we have the optimal pH is 6.5. Then the best genetic models is the best fit for genetic model was the pseudo second order. So it means that this suggests that semi-curve semi-sorption is the rate limiting stop. Then we did the fitting for the isotime absorption, and the best was the Freundlich. And it means that the absorption is on a heterogeneous surface. For the result for the ciprofloxacin, we have the same spectrum, but you can see that the lime green is from the CIF8 polypyrrole, and it means like remove most of the contaminant. So we did a pH study, but the pH study has the same results for all the all the pH, so it's not to affect the absorption. So equaling for the red Congo, the best fitting for the kinetic model is the pseudo-second order, and in this case for the isothermal absorption doesn't have a good fitting, so we need to work more in this part. So for conclusions, we have the base of the synthesis condition in the nanocompost appearance. The presence of cis-off-joint polypyrrole in the was confirmed we corroborate these ones with the XRD and FTIR. In absorption experiments for ciprofloxacin demonstrate that the process is a pH dependent, exceeds up to the 60 from removal, and a pH of 6. Sorry, this is for red Congo. And genetics experiments show that absorption is rapid, starting to stabilize after 7 hours. And regarding the isothermal models, was the Freundlich model now is the best fit, with a maximum absorption capacity at 66 milligrams per gram. And for the ciprofloxacin, genetic experiments indicate that the absorption is rapid, beginning to stabilize after 3 hours. And for future work, we have to analyze other absorption isotherms model to the ciprofloxacin experiment, and we want to do the conductor residuability experiments for CA polypyrrole and determine the 0.0 change as the textural parameters analysis. And for me, it's everything. Thank you so much.
Any questions? If there.
Thank you very much. I have a very quick question. Do you have in mind already how you are going to do your reusability tests?
Not really, because I'm looking for in the papers and I'm reading how is the material working with the contaminants, and after that I am thinking to change maybe the pH, but I'm not sure because I am working with MOF, and acid pH is bad for the material. So I need to learn more about it.
Okay, thank you.
Any other questions? If not, please join me in thanking our speaker one more time. And our last speaker is Adriana Villa Rodriguez from Michoacan University of San Nicolas de Hidalgo. And she will tell us about cadmium absorption mechanism by effective evaluation of hematite functionalized cellulose particles.
Good afternoon. My name is Adriana Villa Rodriguez. The title in the presentation is Cadmium Absorption Mechanism by Effective Evaluation on Hematite Functionalized Cellulose Particles. Well, where does cadmium come from? And cadmium comes from the industrial discharge, electronic waste, and mining. In Mexico, cadmium pollution is mainly due to mining, fertilizers, and battery waste. Where is cadmium going? Well, cadmium gets into the water, water toxicity, bioaccumulation, health effects. There's are impacts on the environment and negative effects in humans. For example, stomachache, vomiting, diarrhea, emphysema, and lung cancer, kidney stones, bone problems, and sometimes death. So there are several methods for removing or eliminating toxic metals from water. But not all industries have wastewater treatment methods. Generally, due to the high cost of technology and maintenance. However, the absorption is characterized by its efficiency and low cost. So, in this particular case of research, the objective was to obtain and develop material. Each absorbent is this material, and in this hybrid because it's composed of both organic and inorganic matter. Looking at the micrograph, the figure shows hematite nanoparticles deposits on cellulose macrophages. So the absorption process is also described by kinetic and equilibrium models, resulting in a heterogeneous surface and progressive chemical absorption in monolayer formation in high affinity and specific sites. And the proposed mechanisms for cadmium absorption are cation exchange and complex formation, van der Waals force, and hydrogen bonding. The cation exchange, which occurs of carbonyl groups or and hydroxyl. Another mechanism, the complex formation with carboxyl in hydroxyl group mostly and build ligand. And fissorption, no, sorry. In precipitation, the precipitation occurs only in alkaline system. And finally, the conclusion, the surface charge is determined by the chemical composition on the surface group and the absorber layers. It begins with rapid physical interaction, continues with chemisorption and heterogeneity series. Thank you for your attention.
Questions for our speaker? Okay. If there are no further questions, please join me in thanking our speaker one more time. I have one announcement to make before we go to the dinner. The dinner is the next gala dinner. I have here a list of awards for the speakers. So in no particular order, I'll announce them. Catherine Mirvika. Oh, I don't know, maybe come up here, I guess. I don't know. Conchi Anya. Romy M. Ettinger. Rie Makiura. Julia Aguilar. Katerina Vogt. Annette Condor. Carlos Wolfolk. And myself. That concludes our afternoon session. So please join me in thanking all our speakers for the afternoon. And we look forward to the dinner tonight, to the gala option. Thank you. Bye-bye.
So by the way, we have a bus like last night. Okay. Thank you.